Good morning, everyone. I, Lovely Singh, convener of the International Webinar on New Research Trends in Functional Physics, welcome you on the third day of NRTFP 2020. In the past 2 days, all your presence made our session excellent, and we do hope the same for this day today. So may I invite our first speaker for today's session is Dr. H.J. Wu. Before he starts, I would just like to give you a brief introduction about Dr. Wu. Dr. Wu has completed his PhD in the year 2013 from University Malaya. His research interests includes polymer electrolytes, which are used in batteries, supercapacitors, and solar cells. He had published more than 30 research papers and secured research funds from the University of Malaya, Malaysian government funding agencies, International Fund from Asian Office of Aerospace Research and Development, Japan. He serves as the treasurer of Institute of Physics, Malaysia, and also involved in organizing international conferences, Solar Asia in 2019. I would like to invite Dr. Wu for his first session on this. So please welcome Dr. Wu.
Thank you.
Thank you, sir.
I'm sorry for the camera. I don't know what is the reason. It is not on.
Okay, no issue. No issue, sir. Please continue.
Okay. Yeah.
Yes.
Okay. Can you see my screen?
Yes. It's fine, sir. It's fine.
Okay. Thank you. Good morning to all my distinguished guests. First of all, I would thank Professor Banik, the Vice Chancellor, Professor Tripathi, the Dean of Basic Science, and of course, Dr. Nilesh, the Head of Physics Department and the Chairperson for this international conference. Thank you also for all the organizing committee members for all your hard work to organize this international conference. All right, I would like to start my talk with this presentation, Innovative Polymer Electrolyte based on polyepsilon caprolactone. First of all, I'd like to introduce myself. I am H.J. Wu. I'm from the Center for Ionics, University of Malaya, Department of Physics, Kuala Lumpur, Malaysia. Malaysia is one of the 11 countries of Southeast Asia, one nation with multi-races and therefore multi-cultures. In terms of time zone difference, I think India and Malaysia, there's a difference of 2.5 hours. And University of Malaysia is located at the capital center of the country, Kuala Lumpur. And and the picture on the right bottom here is the members, some of the members and students of the Center for Ionics, University of Malaya. And there's the man in the middle here is my guru, Professor Abdul Karim Aruf. He is the founder of the center and who has just retired last year. So let me shortly introduce what we do for our research center. Our research focus started with polymer electrolytes. We spent quite a while to study and understand the conduction mechanism, the transport properties, and also the electrolyte and electrode interface. And we also try to make these homemade polymer electrolytes for energy devices application, such as solar cells, supercapacitor, and batteries. So later part of the work, we focus on one of the branch is solar cell applications. We synthesize the sensitizer material, the photoanode, as well as the counter electrode, and then test it with our homemade polymer electrolyte. Another branch is lithium-based batteries, where we synthesize the cathode material, the anode material, and also test it with our homemade polymer electrolytes. The third branch would be the electrochemical double layer capacitors, EDLC. I think like in day one, Professor Hashmi, we in Malaysia we try to make use of the durian shell and the durian seed to activate it, make it as the activated carbon source, and then we use it to test with our homemade polymer electrolytes. Likewise for fuel cells applications. This is the outline of my presentation. I will start with a brief introduction of polymer electrolytes, the selection criteria of the polymer, and characteristics of salt. After that, I'll talk about biodegradable polyepsilon caprolactone, PCl, and some results of polymer electrolytes based on this material. What is a polymer electrolyte? Electrolyte basically is a medium, like a highway, for the charges to transport from one point to another point. When appropriate salt is introduced and dissolved in a solvating polymer matrix, it forms polymer electrolyte that can provide electrical conductivity. Generally, there are three types of polymer electrolytes. First of all, the solid type, PE, where it involves only two main components, polymer itself and the salt. We can also make it softer by adding plasticizer or add in more solvent, make it in gel form. So that forms the second type. And the third type is we add in more metal oxides material, composite material, make it a composite polymer electrolytes. What are the advantages of polymer electrolyte? Well, polymer itself is very lightweight in nature because you make it in a thin film, solid type. Therefore, it suffers no leakage issue and mechanically stable. If you can make it softer a bit, which you can fold it, there is a flexibility for packaging design. And generally, it has higher voltage breakdown compared to liquid electrolyte. We talk about two main components for a polymer electrolyte, the polymer and the salt. What is the selection criteria of polymer as a host? Can all types of polymer work as a host in polymer electrolyte? Well, one of the important factors for the polymer to work as a host is it must contain polar groups, which can act as electron donors. For example, atoms that possess lone pairs of electrons, so that it can form a dative bond with the cations of the salt. The second criteria is the low glass transition temperature TG. If they possess very low glass transition temperature, lower than room temperature, during the application at room temperature, the polymer will behave at their amorphous state and rubbery, soft and rubbery. That enable the polymer segment motion to assist the ionic conduction. The third point is they should have a high dielectric constant, the relative permittivity epsilon. Why is that so? Because that will help to solvate the salt, because the effective distance of ion pair formation depends on this value. I'll talk more about this later. Let's take some examples of polymer. One of them is a famous polyethylene oxide PEO. This polymer has one oxygen atom in the monomer where it contains two lone pairs of electrons, one pair here and a second pair here. This is PAN, polyacrylonitrile. PAN contains one atom of nitrogen with two lone pairs of electrons. While PVDF here, it has two fluorine atoms, and each of them has three lone pairs of electrons. And all these are responsible to form possible complexation site with the cations of the incorporating salt. Next examples are PVA, polyvinyl alcohol. Again, there's one oxygen atom in the monomer that contains 2 lone pairs of electrons. PVC, polyvinyl chloride, with 1 atom of chlorine with 3 lone pairs of electrons. These are very important because it is responsible to form dative bond with the incorporating salt. Other examples, such as PMMA with 2 oxygen atoms, PVDF HFP with 8 fluorine atoms, where there are many possibilities to form complexation site with the cations. I also would like to share about this chitosan because this is a very interesting polymer, a natural biopolymer derived from chitin. And it is the second most abundant natural polysaccharide on Earth. It means it has low cost. If you look at the monomer of chitosan, it contains 4 oxygen atoms and 1 nitrogen atom, where all these can actually form complexation site. Our center has spent some time using this material, but it is not easy because it is hard and not easy to dissolve in most of the solvent. Therefore, modification must be done prior to use this. Another biopolymer is cellulose. This is the most abundant natural polysaccharide on Earth. It has 10 oxygen atoms. So in principle, they should be able to form complexation with the incorporating salt and be used in polymer electrolytes. However, it suffered a similar problem as chitosan because of the solubility issue. So something must be done to modify it so that it can dissolve easily in solvent. Okay, we have talked about the functional groups of the polymer. Now we talk about glass transition temperature, TG. What is TG? TG is the temperature at which the amorphous state of the polymer is converted in between rubbery state and glassy state. Above TG, the polymer is in rubbery state, which is soft and flexible in nature. But if it is below glassy state, it is hard and rigid. Therefore, a good polymer for polymer electrolyte systems would be a polymer with low TG, because low TG, when we run the experiment at room temperature, the polymer itself is in rubbery state, soft and flexible, where the polymer segment motion can actually assist the ionic conduction. Here is a list of polymer with TG and TM information. This is TG, glass transition temperature. This is melting point, TM. As you observe, for example, PEO has low TG, -64, below room temperature. Therefore, this is one of the most popular polymer hosts used in polymer electrolyte systems. Some polymer, for example, PMMA, has high TG, but it can contribute good mechanical strength to the polymer electrolyte. Therefore, if we are going to use PMMA, we must blend this polymer with another polymer, for example, PEO, with low TG, so that the net blend system still have a low TG compared to room temperature. This is one strategy. So basically what people do for blending is they would look for 2 materials, at least one with low TG, so that the blend system has a low TG effectively. Next, we talk about the dielectric constant of the polymer. Generally, most of the polymer by nature, it has quite low dielectric constant value. For example, PEO with 5 dielectric constant value. PMMA only 2.6 at 1 megahertz frequency. That's why in the second type of the polymer electrolyte systems, people add in plasticizer, material like EC or PC, to increase the effective dielectric constant of the systems. Why is it so? Because this value, epsilon here, will actually contribute to the effective distance for ion pair formation. I'll talk about that when in the later slides. Next, we'll talk about some characteristics of salt for polymer electrolyte systems. Examples of popular salts being used in the literature are listed here. Mainly lithium salts. Some of them is ammonium type salts. Dissociation of salt. We talk about mixing salt with polymer. We want to dissociate salt so that the free ions can freely move in the system. But what are the factors? Well, first of all, it depends on its lattice energy of the salt. It is defined as the energy required to completely separate one mole of a solid ionic compound into gaseous ions. Second factor are solvation state of the ions. It means the amount of energy released when one mole of the ions undergo complete hydration in aqueous solution. How can we calculate the lattice energy of salt? Well, lattice energy in general is proportional to Z plus, which means the charge of the cation, times Z minus, the charge of anions, divided by R, which is the sum of radii of both cations and anions. Yeah, based on these equations, the lattice energy is proportional to the magnitude of charge. The higher it is, you'll give us higher lattice energy. And reciprocal to the R, the distance between the ions. That means the size of the ions is inversely proportional to the lattice energy. So the smaller the size, the higher the lattice energy. So in polymer electrolyte systems, we want salt that has low lattice energy, because low lattice energy simply means it can dissociate easily. It has high dissociation rate. And that means once it dissociates into the polymer electrolyte systems, it has high concentration of charge carriers that is freely moved, the free ions. And most likely, when that happens, high concentration of charge carriers will provide high conductivity value. At the same time, we must be aware that the mobility and number density of charge carriers are two important factors determining the conductivity value. There are basically four methods to calculate lattice energy. We will use the last method, the Kapuscinski equation. Well, basically this equation has some assumptions that it has made, which is the ions is treated as spheres, perfect spheres. So this is an approximation calculation. An example of the equations is given here. Lattice energy U is equals to the whole equation as shown here, where V represents the number of ions per formula unit. For example, if it is sodium chloride, NaCl, the V number is 2. For CaCl2, the V number is 3. And Z plus is the magnitude of the charge of the cation. Z minus is the magnitude of charge for anions. R plus, the ionic radii of cation. R minus represent the ionic radii of anion. With this, for example, we compare two types of salt with the same anion but different cation. The first one, lithium perchloride, LiClO4. So once we substitute the value, we obtain 717.5 kilojoule per mole. What about ammonium perchloride? This salt have the same anion, which is perchloride, but different cation. In principle, the cation size is larger compared to lithium. As a result, the lattice energy for this material is 576.6, much lower compared to this. That means, in principle, this salt can dissolve in the same polymer with higher dissociation rate. It may mean higher concentration of free ions in the system. This is a list of calculated lattice energy of various salts using Kapuscinski equation. So in terms of selection of salt, I think this is one of the way we look at the list and compare and select which we want to use. Okay, I will talk about biodegradable polyepsilon caprolactone now. What is this material? Well, this material is made from the ring opening of the monomer epsilon caprolactone and become this formula. Now, you must be careful because similar chemical formula also comes from gamma caprolactone with a monomer structure like this, and also delta caprolactone with monomer structure like this. So for this is epsilon caprolactone. I stumbled upon this material about a decade ago. At the time, people talk about this material is one of the forgotten polymer in the 21st century. If you look at the publication list, this is the latest one that I found it yesterday. You see the exponential trend of the publication in Scopus record that shows how popular is this material. This material is popularly used as in root canal filling, drug delivery, sutures to stitch the wounds, and a scaffold to promote regeneration of tissues. Why is it so popular? Because it has very good biocompatibility with human body and bioresorbability. It also has tolerable degradation kinetics and mechanical properties. You can make it to degrade in 5 years' time or in 1 year time. You can change it easily. You can engineer it according to what you want to do. And it can be processed easily, manufacturing and shipped. If you look at the chemical structure, it has actually 2 oxygen atoms with 2 lone pairs of electrons. Would it be possible for us to use this as polymer host in polymer electrolyte systems? It also has very low glass transition temperature, -60, as low as BEO, way below room temperature. Let me share some of our results of this polymer electrolyte based on this material. The salt that we use here is ammonium thiocyanate with quite low lattice energy, 661 kilojoule per mole. This we use it because it will provide protons as the charge carrier. We also form another system by adding a plasticizer, ethylene carbonate, EC, with dielectric constant of 89.8 and with molecular dipole moment of 4.9 D. Well, with this information, EC basically is a good plasticizer material and also a good dissociation agent for the salt. We will be expecting more and more ion pairs of the salt to dissolve, becoming free ions in the system. Let me share some of the results here. This is ionic conductivity value versus salt concentration. The highest conductivity value for this solid polymer electrolyte system is achieved at 26% of the salt content at a value of 3.94 times 10 to the power minus 7 Siemens per centimeter. Quite low value. We also study some of the conduction mechanism via its electrical properties. So we plot the relative permittivity, or so-called the dielectric constant value, against as a function of frequency. And we found the variation, the changes or variation of this dielectric constant value against the salt concentration actually follows the trend of the conductivity. What do I mean by that? So let us just draw a line. For example, 30 kilohertz frequency, and take all the value of the respective dielectric constant at various salt concentration, and then plot this value against salt concentration. So as you observe here, the triangle represents the 3 kilohertz frequency value of the dielectric constant, and the round shape here, circle, represent 30 kilohertz dielectric constant taken at 30 kilohertz. And as we plot against salt concentration, the trend, which is increasing at the maximum at 26% before it drops. So the trend is actually the same. What does it tell us? What does this dielectric constant, or the real part of relative permittivity, represent? Well, it represents the amount of stored charge in the system. So in this case, it means the amount of stored charge at 26% is the highest, and that contributes to the highest conductivity. We also plot the loss tangent curve as a function of frequency, and we observe peaks at various respective salt content. Individual peak, there is a peak frequency, and we can use that value to convert and obtain our relaxation time T. And then we plot the relaxation time against salt concentration, and then compare it with our conductivity trend. And we found that the relaxation time decreasing until the minimum at 26%. At that point, we achieve the maximum conductivity value. What does it mean? What is this relaxation time means? It means the time taken for the electrons to come back to its original state from disturbance. So the time taken is very short for 26% salt. At the same time, we also normalize the peak of loss tangent and electric modulus M, and compare it, plot it on the same graph. We plot for the imaginary part of impedance, normalized to peak. We plot electric modulus M, normalized to peak, and also loss tangent delta, normalized to peak. And you found the M peak and the loss tangent peak, they fall onto one another at the same point. That means there is a coupling effect between the conduction relaxation peak and the polymer segment motion relaxation peak. So both are working and assisting one another in ionic conduction. We also run temperature-dependent study using Vogel-Tayman-Faucher VTF rule. Now, based on this rule, there are two parameters I would like to take your attention: parameter A and B. Parameter A here represents the pre-exponential factor, and it reflects the number density of charge carriers in the system. Let us now plot the temperature dependent value. This is temperature dependent conductivity at 32 wet% salt. It is a slight curve up, and then once we fit it with VTF formula, this is what we obtain with a good regression value around close to 1 unity. With that, we obtain parameter A information. Every line contributes to parameter A, and we found that the trend, the value of A keep increasing until 26 wet%. Now, A represents the number of charge carrier, right? And this is in agreement with our earlier observation via the relative permittivity observation and also the coupling effect observation. Next, let me show you some of the XRD results. This is our X-ray diffractogram for various salt percent. And let's take one example. All the XRD pattern shows a hump that represents the amorphous domain of the polymer, and 3 sharp peaks represent the lattice structure of 110, 111, and 200. With this information, we use some software to separate or deconvolute the area under the curve of these 3 individual sharp peaks from the broad halo. Using this equation, we calculate the degree of crystallinity. IC represent the area under the curve or the integrated area under the curve for the sharp peaks. IA represent the integrated area of the amorphous domain, the broad halo peak here. With that, we obtain this figure. So the degree of crystallinity keep decreasing until wet% minimum at wet% 26 before it increases. This observation is in agreement with our differential scanning calorimetry results, where from the melting point, you can calculate the relative crystallinity value. And the trend is exactly the same as what we obtained in XRD. That means the semi-crystalline material of the PCl, upon incorporation of salt, the amorphous domain somehow increases until 26 wet%, and that contributes to the highest conductivity. We also have done some transference number study with a DC polarization and AC impedance test for blocking and non-blocking electrodes. And applying this equation, we will obtain a transference numbers of 0.21. So that means the proton transference number in these systems is 0.21. Not high, but is comparable to what has been reported in other systems in the literature. We also try to study the interactions between all the materials with Fourier transform infrared spectroscopy. Well, basically, IR spectra shows the formation of the complexation site at this region, the formation of the loosely bound hydrogen bond between the functional group of PCl, the carbonyl group, and hydrogen atoms, the proton from the salt. And then from another region of CN stretching mode of the salt between 2030 and 2090 wave number, we also deconvolute the free ion, contact ion pair, and ion aggregates percentage, and this is what we find. Basically, the triangle represents the free ion percentage, while the circle represents contact ion pair, and the cross here represent the ion aggregates. So the number of free ions basically increased until a maximum at 26 wet%. So now we confirm. We can say safely the increase of conductivity is due to the increase of number of density of free ions, which is in agreement with all other observations from IR here, from XRD, from DSC, and electrical properties result. Then we go on to add EC in our system because the conductivity value is too low for any application. So with addition of EC, the polymer, the thin film becomes soft and rubbery, like shown in this picture. And the conductivity increases until 10 to the power of -5 Siemens per centimeter at 50 weight%. Beyond that, the polymer is no longer mechanically stable. Again, we plot the relative permittivity, the real part, as a function of frequency, and then we select a field frequency and then obtain the value for various salt concentration, for various EC concentration, and then we plot this curve. Why are we doing that? Now, because this value represents the amount of stored charge in the system. We want to find out whether what actually causes the increase of the conductivity, because the amount of salt is fixed for all the systems. It's fixed, it's the same. We are just adding more and more EC. What is the effect of EC addition into the systems? Well, here predicts the increase of charge carriers. How could it be? Well, if you look at this formula, this R represents the critical distance ion pair formation. That means below this value, it is most likely the ion pair will form, okay, in the systems. Above this value, it is most likely remain at free ion state. According to this formula, epsilon prime, the real part of relative permittivity, is here. That means the higher the value, the lower the R. The higher the value of the whole systems. Now, this value is not belongs to EC. Yeah? This value comes from the system. The higher the value, the lower the value of R. The lower the value of R means it is unlikely for cation and anion in the system to form ion pair formation. That means the dissociation rate of the free ions is expecting to increase with addition of EC. Here shows the temperature dependent study. Again, we obtain a curve moving up with increasing temperature. Then we use a fitting method to fit this with VTF. We plot another graph and obtaining a straight lines. From the gradient, we obtain some parameter of A and B. Similarly, parameter A shows increasing trend. Now, parameter A reflecting the amount of charge carriers, the concentration or the density of the charge carriers. So it's increasing trend, which is in agreement with earlier observation from the dielectric constant value. What about from IR spectra? We deconvolute it between this region 2030 and 2090, because within this region, the CN is responsive to the IR radiation. And after we deconvolute it, separate the free ions, ion pair, and ion aggregates, we obtain this curve. The triangle represents the amount of free ions concentration against EC concentration. As EC increases, the number of free ion increases. That means EC has successfully dissociated more and more ion pairs from here into free ions. At the expense of the increase of free ions is at the expense of ion pair and also ion aggregates. What about XRD calculation? We apply the same deconvolution, separating the 3 sharp peaks and the broad halo, and calculate the degree of crystallinity. This is what we obtain. It decreases from 33% to 16%. At the same time, we run DSC. From DSC, this is what we obtain. There are new peaks and new shoulder peak at TN. What does it represent? It means it gives us a hint that EC addition to the system actually has formed complexation, not only with the salt, but also with the polymer. So this gives us a hint that we need to do a thorough FTIR investigation in between EC and the salt, EC and polymer, and EC with the polymer electrolyte systems. This is what we did. After lengthy of investigation, this is one example of the IR spectra with 0 to 50 weight% in the region between 1005 to 1900 weight number. We observe new peaks increasing with EC concentrations. At the same time, new shoulder appears. That means they give us a clue to draw this diagram. Now, from IR, certain new peaks represent the new complexation site of the EC and the polymer itself. And that is via the carbonyl group. So EC here will interact with the polymer via the carbonyl group, as indicated in the IR in the region of 1700. And at the same time, EC also interacted with the salt cation via its oxygen atom. So with this in mind, we found that the increase of conductivity is not only due to the increase of charge carriers, but probably the migration or the ionic conduction path is shortened because the hopping distance for the ions possibly becomes shorter with the assistance of EC, because EC provides more complexation sites, more stations for the ions to hop around. Therefore, the conduction path should be shorter. We also have done some SCM analysis. Basically, PCl-based polymer electrolyte gives a quite nice SCM micrograph like this, with a lamina as a bicycle spoke, form a spheroid. So one of this is a spheroid with a new growth of nucleation from the center with lamina as the bicycle spoke. So this is what you obtain. And this size is become larger and larger. With incorporation of EC, we observe that eventually the spheroid disappear. That means the increase of the amorphous domain. So in conclusion, the effect of EC into the system not only increase the dissociation rate of the salt, but also it reduces the conduction path. Therefore, it gives the ultimate increase of the conductivity value. We also have tested PCl-based polymer electrolyte with lithium salt and ECPC plasticizer, make it in the gel form, and obtained certain conductivity value in the region of 10 to the minus 3 Siemens per centimeter, and then we use it to test it in EDLC using our homemade activated carbon from durian shell and durian seeds. Yeah, I think this is what we obtained, quite low specific conductivity of 15.8 farad per gram. Yeah. Okay. Towards this is, I'm going to end my presentation. I would like to acknowledge the financial support from the University and Ministry of Education Malaysia. Also, would like to thank the team members within the research center. And with that, I thank your attention. Thank you very much.
Thank you for your nice talk. And any questions from any speaker?
Yes, sir.
Hello.
Am I audible?
Hello.
Yes,
Hi.
yes, you are audible.
Hello, Wu, sir.
Yes, good morning.
Hello, good morning, sir. Can you go back to slide number 37?
37, okay.
Yes, sir.
Let me present now.
Sir, in that slide, you have shown a curve in which there was an area, and you showed that free ion area is maximum. So conductivity is because of free ion.
Hold on. This slide, am I right?
37. Yeah, yes, sir. The last one.
Okay.
Yes, sir. In last figure, you were saying the peak area is maximum for free ion. So conductivity is because of free ion.
Okay. This slide represent, let me see, this is a PCR sort system. Okay. So the triangle here represent the number of free ions. And according to the trend, the number of free ions increases with addition of salt and maximum at 26%. Yes.
But
So,
sir, the contribution
yes.
from contraction pair is maximum, is higher as compared to free ion.
Yes, you are right.
What do you have to say over this?
Yeah, we believe the contact ion pair, which is neutral, do not contribute to conductivity.
Okay, sir. Okay.
Yeah.
Okay. Yeah. Thank you, sir. Thank you.
You're welcome. Thank you for the question.
Hello.
Yes.
Hello.
I
Am I
am
audible, sir?
Yes, sir. Yes, sir. Audible.
Okay. Sir, during the synthesis of this system, which solvent you used for
In
the
this,
formation of polymer electrolytic film?
okay, good question. In this case, we use THF,
THF.
tetrahydrofuran. Yeah.
Okay. Sir, earlier I also tried to synthesize PCl-based polymer electrolytic films using THF, but
Yes.
sometimes I saw that film form are breakable in nature, not transparent, and some
So
pores
just
are
only
there
have
also.
one.
Okay. Yeah.
So can you just suggest me any kind of the synthesis improvement in the synthesis process?
Yeah. Because THF has a very low boiling point, around 60 degrees C. Am I right?
Okay.
Yeah. So I think during the drying time, how the evaporation when you mix it before you leave it to dry at room temperature, how do you dry it?
Yeah.
May I know how do you how do you prepare your sample?
Yeah.
Yeah.
I
I think
I
you have
dry it
to,
at room temperature and after putting in the desiccator for further drying.
yeah. I think the environment for the polymer electrolyte formation is very important. In this case, because THF has a quite low boiling point, it's very
Okay.
volatile. Therefore, you may want to try, because in our case, we actually do not leave it dry in the open space. We actually
Okay.
leave it dry under a controlled environment
Okay.
at about 40 degrees C for some time, so that the thin film will slowly form,
Okay.
and you will observe a very nice spheroid under SEM. Yeah.
Okay. So maybe it may be due to the rapid evaporation of the solvent, like that,
Yes. Yeah.
if we dry in the open atmosphere.
Yeah. Sometimes I think there is also a fluctuation of your temperature depending what season you are in your country, in your lab at the time.
Okay.
I have one small question. Are you hear me?
Yes, sir. Yes, sir. Your audio will continue, sir. You can ask.
First question is, you have presented your dielectric results for only particular 3 frequencies. What is the particular reason for this only these frequencies?
I'm sorry, I can't hear clearly. Can you repeat your question?
You have presented your result, and in introduction section, the dielectric value of some polymers like PVDF and PCl in the particular fixed frequency like 3 Hz, 300 Hz, 3 kilohertz and 30 kilohertz. What is the reason for taking these particular frequencies?
I'm sorry, I can't. I think the line is not good. I can't hear clearly. Would you mind to type? Maybe you can type. You're asking about something in the introduction. Am I right?
Yes. You have regarding the dielectric value of some polymers.
Yes. Dielectric.
Like PEO, you have mentioned PEO, PVDF. For PVDF, you have mentioned 7.6 most probably at particular frequency. What is the reason of that only single frequency?
Oh, okay. Because if you look at, let me show you some of the. When we are plotting, can you hear me?
Yes, yes.
Okay, when we are plotting the epsilon prime, the real part of relative permittivity or dielectric constant, so to speak, we observe there is a very high value at low frequency, and it decreases drastically with increasing frequency. So in this case, even though we thought it's a flat after log f number 3, right? But if we maximize it, you observe this. There are still values up to log f4 and 5. So this value actually is dependent on frequency. It is a function of frequency. The reason why the value is high and low frequency is due to the electron polarization effect, because as I mentioned, it represents a stored charge in the system. So when at low frequency, because you're testing it for EIS, it's the AC. So when the polarity between electrons, the changing of the polarity plus to minus, slow enough at low frequency, the charge has sufficient time to accumulate at the electron interface. Therefore, at low frequency, we observe many charge line up at the double layer, right? That form the double layer. So that contributes to the electron polarization effect with high value. But as frequency increases, the charges has less time to react according to the fast flipping or polarity change between the two electrons. Therefore, the value reduces drastically. Now, at the same time, in the system, there are more than one type of dipole. One is come from the salt, another one comes from the polymer. The dipole of the polymer, basically, they don't move they don't have translational motion, but they actually only rotate. So you just imagine your cloud of electrons in your functional groups. For example, oxygen, you have 2 lone pairs of electrons. It actually rotates. So the partial negative and partial positive actually rotate in your polymer bond. That also contribute to this value. Then now come back to your question. Why for the pure polymer, oftentimes what are we given the value for the dielectric constant is actually a function of frequency because of this reason. I hope I have answered your question.
Okay. The second query is, you have mentioned for the EC, when you mix the EC up to 60%, then the ratio of the polymer and EC are maintained or only fix the ratio of the polymer and you increase the ratio of the EC? abruptly?
Oh, okay. We add EC up to 50% because beyond that, the film itself become more jelly-like, like gel type, which is not what we want. We want it to be still in thin film, a soft, rubbery thin film. That's why we stop at 50%. Yeah.
No, but the ratio of the polymer is decreasing when you increase the ratio of the EC.
Are you asking me, did I increase the the EC concentration?
Have you maintained the concentration of both are fixed?
Oh, okay. For this system, EC, I have add equal amount of salt for all EC content, which is 26% of salt.
Okay.
The amount of salt is equal for all the system.
Okay. Thank you.
Yeah. Thank you for your question.
Okay, hello sir. Actually, I have a small question.
Okay.
In your plot, PCl NH4S solid polymer, there is a plot salt concentration versus a log sigma.
Okay.
So first increase the concentration of salt, so conductivity is increases.
Yes.
But after certain concentration, it goes to decrease. What is the reason, actual reason behind it? What is the science behind it? Can you tell me the physics behind it?
Yeah.
Yes. Below, back.
So what?
Yeah. Yes, sir. Yes, this plot is. I'm asking this one.
Okay. Yeah.
Yes.
So, yeah, the many literature reported that it is due to the number of free ion decreases because as more salt is dissociated into the system, it gets too close to one another, and it will form ion pair or even higher ion aggregates. Then in order to quantify this observation, we actually tested it we started it with our IR spectra. Wait a minute, where is it? Oh, I think it's here. Yes. The increase of, if you look at this diagram, the increase of conductivity up to 26% is due to the increase of free ions. You can see. And right after this, it decreased. So we are of the opinion that the decrease is due to when more and more ions dissociate into the same system, same amount of system, same volume, it gets too close to one another, and it will form more ion pair here. Ion pair actually in this case keep increasing. Likewise, ion aggregates here. This percentage of free ions, ion pair, and ion aggregates, we obtain this from IR spectra when we identify the CN stretching mode, because from literature, CN stretching mode, they have very well defined free ions, ion pair, and ion aggregates, which is responsive to IR radiation, so-called a fingerprint. So because of that, we use it, and then we separate the contribution of each of these using some software help and deconvolute it, and we obtain this. So from here, we are quite safe to say the decrease is due to the increase of ion pair and ion aggregates here.
Okay, fine. It's fine, sir. Clear.
Yeah, thank you.
Okay. Thank you very much. Once again, thank you very much.
Thank you very much for all your questions.
Okay, I hand over to lovely madam, convener, please.
Thank you so much, sir.
Okay.
It's our very honor to have you in this session as a plenary speaker. Thank you so much for being with us. Once again, thanks a lot, sir. Now, may I invite our keynote speaker for this session, Dr. Kamlesh Pandey. It's been an honor and a huge privilege to have you here, sir. And me and my team welcomes you in this session as a keynote speaker. Before Dr. Pandey starts, I just wanted to give you a brief introduction about Dr. Pandey. Dr. Kamlesh Pandey has completed his PhD in the year 1995 and postdoctoral studies from Banaras Hindu University, currently City of Allahabad, a premier high-pressure temperature institute of the nation. He has published more than our keynote speaker, Dr. Kamlesh Pandey. Welcome you, sir.
Thank you. Are it be audible?
Yes, sir, you are audible.
And
Please go ahead.
say screen.
Screen not audible, sir. Please.
Sharing is not open here.
Please click on screen only. That
Present now.
yes, present now.
Your entire screen.
Yes, entire screen. And single click on screen.
Okay.
Okay.
Thank you, Nilesh sir. And I would like to thank first to organizers for inviting me for the keynote speech in this session. I am from University of Allahabad, and the famous some pictures of this in Allahabad is the picture of Kumbh. Now we go to our talk structural studies on biodegradable polymer electrolyte developed with multiferrous solvent. This talk is important because in the polymer electrolyte research, everyone says that our film is dried. But there is some confusion, like if we say that our film is dry, then what happens about the solvents? Are these solvents are fully removed or partially removed? Are you looking? Hello?
Yes. You are audible and looking. No issue, sir. Continue, sir.
Okay.
Please.
Okay. Then it is very important question. If the solvents are present in the polymer electrolyte, then it have any effect on our measurements or not? This is the important question. Yesterday, I have asked some questions regarding these solvents, and today you have also seen that Mr. J.P. Sharma ji has asked about the solvent of THF, why his film is brittle. Can you expect that these solvents show some important role in formation of the film, and after the formation of film, it gives some modification in the structure of our films? In this study, we have correlate the experimental results with the theoretical results in some polymer electrolyte. That polymer electrolytes are the biodegradable polymer electrolytes like polyvinyl alcohol and polycryptolactane. Membrane technology has very important for the recent years due to their benefits such as easy control, flexible, simple operation parameter, high through output, and automation. Now, what is the polymer and why this polymer is so important? Now, these polymers are mostly the insulating. They have the behavior of insulating behavior. To modify these behavior, we take some material and dope in that polymers, and after that we have done some other modification like plasticization, like in dispersion of filler, etc. And then we make a material which is applicable for the device in industrial, medical, or the technical applications. Now we come to the polymer electrolyte. Polymer electrolyte is a very new class of material. In this material, we have learned in previous lecture that the important role of glass transition temperature. The glass transition temperature can modify the behavior. For the sake of convenience, we have learned in earlier lecture that if we take a polymer which has the lower Tg and some polymer which have higher Tg, then we can modify the behavior of these composite polymers by mixing them like PEO and PMMA. PEO has the minus 60 degree Tg, but PMMA has higher Tg, and if we mix, then it gives a separate behavior than the polyethylene oxide and PMMA. Now we can classify these polymer electrolytes as the solid electrolytes. What is the meaning of solid electrolytes? Before 1967, the solid electrolytes are not, and after the birth of the ionics, means the birth of the ionics in 1967, and the father of the ionics in India, Professor Suresh Chandra, has first give a book regarding the solid state of the technical application. Our most important innovation is the mobile or the rechargeable battery. Of these electrolytes, we have made some modification in some different type of polymers. Now we classify these into two categories. One is the organic and second is the inorganic. Organic, the polymer electrolytes and polyelectrolytes. But electrolyte is, it can be make film. We can see that there are some routes by which we can make our electrolyte, that are the gel system. In gel system, we also dissolve these polymer electrolyte into the some appropriate solvent and put in certain temperature and ambient condition, and then we found a jelly-like structure. The factor affecting these modifications are chemical structure, chain configuration, intermolecular interaction of the polymers. This is the interpolymer interaction. There are two polymers. One is here and second is here. I have just mentioned earlier that if we take the one is the low Tg polymer and second is the higher Tg polymer, and if we mix them, then we can get some better result than the separate or the individual identity of these polymers. This is the concentrated solution, amphipolic polymers, and the polymer dissolution is a process on which we have discussed experimentally what effects have obtained on the polymer electrolyte of the solvents. There are different type of studies in which we found that these process has the one step or two step process. In some cases, it is found that there are two stage process. One is the polymer swelling and second process is the dissolution of the polymer. What is the polymer swelling? When we mix the polymer into a solvent, then we found that these into the polymer chain and try to bind to at a certain position and initially want to swell these polymers. After a certain time or a certain process, it tries to break these chains and make a random structure, and these random structure will individual identity or the amorphous structure or some random structure for each and every molecules. The viscosity of the polymer solution. It depends on the small molecular size, intermolecular interactions, and this viscosity is also affecting our process to develop a polymeric film. Now we come to the solubility factor. Here there are some process or some factors which affect our solubility. First, we try to increase the molecular weight, increase the degree of crystallinity, increase the number of cross-linking, and rate of dissolution start to decrease. These factors are not important for the polymer membrane synthesis. Now we come to our experimental result. Our experimental result is the first we start to study the structural study of this polymeric membrane, and we found that if we make a polymeric membrane, then some structural studies shows that the polymer electrolyte has some different structure after drying or some different characteristic after drying. Then we try to simulate these polymeric membrane or taking the polymer molecules and interact with the different solvents. Then we found that there are something which is important to study for the polymeric membrane synthesis on behalf of the solvent used. Our first system is the polyvinyl alcohol and second system is the polyvinyl butyrol. Now we come to the spectroscopic study of the polymeric system. Case 1 means PVA. Here is the some biodegradable polymers. This theoretical structure of the polyvinyl alcohol. Here we see first is this is the monomer of the polyvinyl alcohol. This is the dimer of the polyvinyl alcohol, and this is the trimer of the polyvinyl alcohol, and this is the tetramer of the polyvinyl alcohol. Why we take these pictures? These pictures show that we try to simulate a structure of the polyvinyl alcohol with some different solvents at 4 positions. First, we take the monomer of the polyvinyl alcohol with some solvent. Then we try to make another interaction calculation of the dimer of the polyvinyl alcohol with that solvent. And third, we try to take the trimer of the polyvinyl alcohol and interact with that same solvent. Similarly, we study the tetramer of the polyvinyl alcohol for the interaction of that solvent. here is the question, why not we go to after beyond the tetramer? The calculation related to the theoretical interaction with four PVA molecule with other solvents is very lengthy and huge. So we are not trying after the tetramer of these PVA molecules. Here is the theoretical infrared spectroscopic calculation and their spectra. Here is the PVA monomer spectra, this is the PVA dimer spectra, and this is the PVA trimer spectra, and this is the PVA tetramer spectra. All these spectra getting by the theoretical calculation, not these are the experimental calculation. And here we found the results, all the peaks mostly present in the experimental results are present in the PVA monomer, PVA dimer, and PVA trimer and tetramer. There are some few peaks which are not present in our experimental measurements maybe due to the experimental error or the limitation of machines or the process of polymer film synthesis. But mostly peaks are present in these experimental peaks are present in the theoretical calculations. This is the second study, that is the Raman study. And here we found that these are the Raman analysis of PVA monomer, PVA dimer, PVA trimer, and PVA tetramer. And these peaks are also correlated with the theoretical calculation to the experimental calculation. And it is found that all the peak resembles with the experimental results. Here we had modified some instruments for the measurement of low temperature and high temperature infrared spectroscopy. We studied these FTIR from minus 10 degrees centigrade to 150 degrees centigrade. For this we use the Bruker alpha FTIR spectrophotometer, and we have homemade these arrangement by which we can lowering the temperature and start increasing the temperature. Here we show this instrument shows the 5 degrees centigrade. Now we come to the some XID spectra, and these are the XID spectra of the PVA in water, DMSO and DMF. There are three type of solvent we are using. One is the water, second is the DMSO, and third is the DMF. And we anneal these films, synthesize with the help of these solvents, and then we take the XID, IR and Raman spectra of these films, and now we discuss step by step all these temperature, annealing temperature effect and their results. Now first case is the interaction of PVA with the water. This is the PVA and this is water. Now we come to the first case. This is the monomer and this is the single water molecule. Now if we take two PVA molecules, means dimer of the PVA, and here is the two water molecule. Third case is the 3 PVA, 3 water molecules. Fourth case is the 4 PVA and 4 water molecules. This is the theoretical structure of the PVA and water. Now we come to the peaks. Here we found all these peaks which is present in the theoretical calculation are not present in our experimental result, because in our experimental result we are not limited our polymer to in a monomer condition or dimer condition or trimer condition or tetramer condition. We take some weight percent of the polymer and mix in a certain volume of water molecule. Then there is no limitation of these monomer, dimer, trimer and tetramer. So, and these first peak in the polymer electrolyte, we have found that these peaks are the broad peaks. We cannot identify the different small peaks without deconvoluting these peaks, and we cannot say how many peaks are merged inside this broad peak. So we are not identifying these small peaks which is obtained by the theoretical results. And this is the broad peak, 3285 is the centimeter inverse is the broad peak here. And it has some limitations that we cannot deconvolute these peaks. And all other peaks are also resembles with the theoretically obtained peaks of the PVA. Different configurations interact with the water molecules. Here is the experimental IR spectra of the PVA H2O at different temperature from 50 degrees centigrade to 200 degrees centigrade. Now, from room temperature to 200 degrees centigrade, we found that there at higher temperature, some peaks breaks into some small peaks, and they are because here after that, if the H2O present in the system, then there is no relation of these peaks. After 100 degrees, single PVA and single DMSO, 2 PVA and 2 DMSO, 3 PVA, 3 DMSO, and 4 PVA, 4 DMSO. Means monomer, dimer, trimer, and tetramer. These are the theoretical interaction picture of the monomer, dimer, trimer, and tetramer. Now we come to the peaks. Here we found that there are some peaks like 234104. This is the OH stretching of DMSO, which also present in the structure after drying the membrane, and it is always present up to 200 degrees centigrade. It means the modification or the interaction by the DMSO or polyvinyl alcohol have some changes in the chemical structure or their structure which can be modified the characteristic of the polyvinyl alcohol. Here is also some water molecules also present which show they are coming from the external source. Now we come to the experimental result of PVA DMSO at different temperatures. These are the IR spectra at room temperature 50 degree, 100 degree, 150, 200 degrees centigrade. And this is the peak assignments of these. Here we found that this peak become a doublet. This is the OH stretching in PVA, and this is the HOH symmetric stretching in H2O. At 200 degrees centigrade, it becomes doublet. 125 degrees centigrade, it is also a doublet. But at room temperature, this is the singlet. Means at the higher temperature, some peaks shows their prominent behavior in the structure of the polymer. Means the presence of solvent is also an important factor which affect the behavior of the polymer electrolyte. Now, similarly, we study the Raman spectra, and it is also found that at room temperature and 200 degrees centigrade, the comparison of both figures, we found that there are some presence of external molecules in the lattice of the polymeric membrane. This is the assignment of the Raman peaks. Now, in the third case, PVA interacts with the DMF. This is the PVA and this is the DMF. Now, we come, the monomer interact with the single DMF, dimer interact with the double 2 DMF, and trimer interact with the 3 DMF, and tetramer interact with the 4 DMF. And these are their analysis. assignments of the peak, and here we also found that there is some traces of the solvents or the traces of the constituent of the solvents are present in the polymeric membrane. This is the experimental IR spectra at different temperature and their assignments. Here we found that these peaks are also present at room temperature and at 200 degrees centigrade and 125 degrees centigrade with slightly different position of their same peaks. Now we come to the Raman study. Here we also found that these peaks becomes more prominent in the case of deconvolution at 200 degrees centigrade. These are their theoretical and experimental assignments. Now we come to the second type of structural studies, that is the XRD studies. In XRD studies, we found that the PVA has the main characteristic peaks at 19.6 degrees centigrade and 22.3 degrees centigrade. And it splits 20.0 degree, 21.9 degree, 22.3 degree, and 22.7 degree for water. And in DMSO and DMF, it is split into these three peaks. At low temperature, these two peaks split in various small peaks. At high temperature, these peaks shift at a higher toothy side. Hence, it indicates the lower crystallinity of the membrane. These are the different temperature XID of the polymer electrolyte dissolved into three different solvents. Here is some important observation. First, we come at low temperature, means room temperature. Here we found in case of the water solvent, here is the nature of peak is the one broad peak and four small peaks. But if we go at higher temperature, then we found that this water dissolved polymer electrolyte have different type of nature of the X-ray spectra. Similarly, if we take the membrane which is dissolved in DMSO, then here is the two almost approximately equal peaks, but at higher temperature, these peaks shifts at different size. Similarly, in DMF and at room temperature, and 100 degrees centigrade, 125 degrees centigrade, 150 degrees centigrade, 200 degrees centigrade, their crystallinity changes. And if we calculate the crystallinity effect, then we found that the crystallinity index of these polymeric membrane is changed like this. This is the room temperature variation and this is their relative crystallinity. Then we found that the film of the water and DMSO is almost same crystallinity at mostly more temperature, but in DMF it had higher crystallinity. As in earlier lecture, one question, why the film brittle at DMF? This is the one reason. If we take the solvent DMF, then we found that due to low boiling point, it evaporates violently and it makes the film brittle. This is the same study, and here we found that the film developed by the water have shown some cracks in PVA. At 200 degrees centigrade, this structure shrinks and make a small structure. Similarly, in DMSO at room temperature and DMSO at higher temperature, contrary to this result, here we found that this structure enhanced is single bricks enhanced like this. But in DMF at higher temperature, this structure does not show any certain pattern. The second case is the polyvinyl butyl. Here we study the solvent acetic acid, DMF, DMSO, and ethanol. The similar result we have obtained in these cases, and we conclude these that if we, here is the solvent DMF, now we come to the THF, and then we found that in both cases, both biodegradable polymer, we have a certain amount of confusion regarding the solvent-free polymers. Means we are now trying to think all these our polymeric membrane is either completely solvent-free or in that matrix there is some traces of the solvent which can show their effects or show their property or modify the property of the polymeric membrane for our experimental study. This is the question for thinking in future. Means solvent-free electrolyte is completely solvent-free? This is the question mark. Our group members are Dr. Kamlesh Pandey, I am also, and Dr. Mrigang Mauli.
That what may be the origin of the external source of water molecule, as discussed in FTIR, even at 200 degrees centigrade.
Yes. If we make a polymer film which is dissolved in the water, that polymer film, water breaks into H plus and OH minus, and this OH minus go into the polymeric chain and try to bind at a certain position. If there is no position vacant, then in PVA is a solvent swollen polymer, it traps into the matrix and always show their presence at higher temperature.
Okay, sir.
Okay.
Any more question? I think there is no question. So thanks Dr. Kamlesh Pandey for giving such a nice lecture, nice talk. And okay, go ahead, Dr. Lovely.
Thank you so much, sir. Thank you, Dr. Kamlesh Pandey, for having an excellent presentation. Now, I would like to invite our first speaker for the invited talk, Dr. Indu Elizabeth. Dr. Indu Elizabeth is currently working as a scientist in CSIR National Physical Laboratory, NPL, New Delhi, in the Force and Hardness Metrology Division. Her research activities include the development of carbon-based force sensors for artificial intelligence and biomedical applications, development of high-capacity anode materials for lithium-ion batteries, etc. She has worked towards the technology transfer of indigenous lithium-ion batteries to industries during her PhD. She has done her PhD in engineering in the field of lithium-ion batteries under the Prime Minister Fellowship for Doctoral Studies in the year 2018. The thesis has won the Best PhD Thesis Award of Academy of Scientific and Innovative Research and in National Carbon Conference CCM 2019. It's my honor and privilege to invite Dr. Indu Elizabeth, scientist, National Physical Laboratory, New Delhi. And today's her discussion topic is anode materials for high-capacity lithium-ion batteries. May I invite Dr. Indu Elizabeth.
Thank you for the invitation. Good morning.
Yes, good morning, madam. You are not visual. Please turn your camera.
Okay, 1 minute. Is my slide visible?
Slide also not visible.
Camera is actually on.
Okay, no issue. But please present now your.
Okay. Present now. I have also opened the slide. It is not coming visible. I'll try once more then.
No, you have to open from your this screen.
I have opened.
Again do it, please.
Okay. I'll join the meeting once more then.
Okay.
Hello?
Yes, yes. You are audible and visual both. Thank you.
Okay, thank you.
Now,
I'll
now
present
present now.
your entire screen, right?
Entire screen.
After that, it is not getting loaded. 1 minute. Maybe that is a network issue here.
Now.
Okay.
Yes.
Is my slide visible now?
Slide not visual, but your screen is visual. So please open your slide now. Yes. Please. Yes, it is visual. Okay,
Thank
fine.
you.
Continue.
Okay, good morning all. I'm Dr. Indu. I work as a scientist in CSIR NPL. And as you all know, NPL is the National Meteorological Institute of our country. That is, we maintain the national standards for our country. And I'll be talking in this talk. I'll be talking about the anode materials for high-capacity lithium-ion batteries in the field which I have been working for like around 6-7 years. And like coming to the presentation, as you all know that the global energy demand is increasing day by day. And from the IEA document, like we can see that about 86% of the energy which is consumed mainly comes from the fossil fuels. And these fossil fuels will be exhausted in less than 10 years. And we know that it is creating problems like air pollution, which leads to global warming and climate change. So because of these problems, like all the nations are like shifting to renewable energy resources. And considering renewable energy resources, even our country, India, we rank 5th in the world in the term of wind energy power, and we have also installed more than 20 gigawatt renewable energy capacity by the year of 2012. But the problem with renewable energy is that if you are using it directly, it is we cannot use it for advanced applications because the supply is intermittent or unstable. That is, only when the sun is there we can use the solar energy. During the night time, like the use of solar energy is not possible. And energy storage system, we can make use of the renewable energy power to the maximum. So in order to use a renewable energy storage for advanced applications like electric vehicles or big applications, we need to have the energy storage system. And considering different energy storage system, batteries are emerging as one of the best candidates for this because of its advantages, like it has high portability, high energy density, medium cost, and then no gaseous exhaust, and it has like high power density. And like we know that the lithium-ion batteries or the batteries which we are now seeing is mainly used in portable electronic devices and like cameras, mobile phone, etc. And they have a low capacity between 50 to 200 watt hour per kg. And they are small size batteries and they have lesser life of 2-3 years. So if we have to use these batteries for advanced applications, like we need to improve the capacity of these batteries over 500 watt hour per kg, and we need to have large size batteries which can last longer and which are cheaper also. And if you're considering the batteries, like the rechargeable batteries, like from the Ragan plot, we can understand that the lithium-ion batteries are having the highest energy density and highest volume density. And it is also lighter in weight and smaller in size. So they are the best candidates. And in comparison, like I can tell that this lithium-ion batteries is having a voltage which is approximately 3 times the voltage of a nickel cadmium battery, and it can store about 2 to 3% more energy per unit weight and volume than other rechargeable batteries. Also, it has a very low self-discharge and low shelf life. Moreover, it can cycle up to more than 2000 cycles continuously, giving it a long life, and it can operate over a wide range of temperature. And coming to the design of a lithium-ion battery, as most of the batteries, like a lithium-ion battery also has an anode, a cathode, and an electrolyte. And the anode used in conventional lithium-ion battery is like usually the graphite anode. And the cathode material is the lithium cobalt oxide, and electrolyte is LiPF6 in EC and DC 1:1 ratio. And we use a separator, which is usually polypropylene or polyethylene. And while charging the battery, what happens is like we connect the battery to a plug, and the lithium ions which are stored in the cathode, that is the lithium cobalt oxide, it moves from the cathode material to the anode material, to the graphite through the electrolyte, and it gets stored in the anode material between the layers of the graphite. And during the discharging, the lithium ions which are stored in the graphite or the anode material moves from the anode to the cathode. That is what happens like while discharging. So from this operation, what we can understand is that anode is a limiting like component in a battery, and the application to which a charged battery can be put mainly depends upon the storage capacity of the anode material. And the life of the battery also depends upon the structural stability of the anode, like whether the anode material is able to withstand large number of charge discharge cycles. So in order to have like high capacity batteries, first we need to improve the capacity of the electrode materials. Then we should have like a high structural stability, and the electrode should be like compatible with the electrolyte and the binder systems, and also like it should exhibit high reversibility. And coming to the commonly used anode materials, as I already mentioned, in the conventional or the commercial lithium-ion battery, graphite is being used as the anode material, and the lithium ions are stored in between the layers of the graphite. But the problem with graphite is that its capacity is the maximum theoretical capacity of the graphite anode is limited to 372 milliampere hour per gram. That means like only up to 372 milliampere hour per gram is the maximum capacity, and it has low rate capability. That means like if you are going for faster charging, like graphite anode will not support faster charging. And then another candidate like which is like in discussion is the metals. And from the bar graph, we can understand that the metals have a very high capacity as compared to carbon. But the problem with metals is that they experience a large volume change when the lithium ions are inserted and deinserted from the metals. Their volume change is more than 300%, and because of this, the structural integrity of the anode is disturbed, and therefore it has limited cyclability. So in order to have like anode materials which to like one of the way to overcome to get these anode materials is to make a composite between the carbon and the metals, so that we can have anodes with higher capacity and higher cyclability. And regarding this we have worked. And another property like what I am talking is like in a conventional lithium-ion battery fabrication, what we do is that the anode material, that is usually the graphite powder, it is mixed with a binder and an electrical current collector. And then a slurry is made, and the slurry is coated onto a copper current collector, and it is done using a coating machine. After that, the thickness of the electrode is maintained by using the calendering process, that is also using a costly equipment. And finally then we get the anode material, that is a copper current collector coated with the electrode, coated with the graphite material. So involves like of the from the done is like we have made a freestanding anode. It means like there is no need of any current collector or a binder to support this. And it can be, and this was made like using multi-wall carbon nanotube. The multi-wall carbon nanotube has high aspect ratios, and so it can form a paper. Like, and this can be made using a simple vacuum filtration technique. The setup is like as shown in the figure. And from this, like which is prepared, it is highly flexible. It can be folded, it can be rolled, but it doesn't tear. So it is highly flexible. It is also less. like metal particles onto it so that its capacity is also improved. And this also can be done with the multi-wall carbon nanotube paper. And we have filed a US patent for this, and it was granted in the 19th of June 2019. And the development of freestanding anodes, first material which we have developed is the antimony sulfide carbon nanotube freestanding anode. It was developed using the hydrothermal process. In the hydrothermal process, antimony chloride and thiourea were mixed in ethylene glycol, and it was heated in the autoclave. And finally, we got the antimony sulfide rods. This was like with pure antimony sulfide. And if you wanted to get like freestanding anode with carbon nanotube, we added like the carbon nanotube also during this process in the autoclave. And then we got the antimony sulfide carbon nanotube rods with CNTs. And then we made the freestanding anode. These are the freestanding anodes which were made. And in the same diagram, like we can see that carbon nanotubes are also there, antimony sulfide rods are also there. With this material, this anode material was made. And this is the XRD peaks in which all the peaks are being matched. And then we cycled this in a like lithium ion coin cell. And like what we could observe is that for the when antimony sulfide was alone cycled, like without putting CNTs, it gave a high capacity in the starting of 350 milliampere hour per gram. But like as the cycle increased, like as the number of cycle increased, like there is a decrease in capacity. Capacity is getting decreased, and it became 293 milliampere hour per gram. And this is mainly because of the like volume change which happens in the metal. As I have already mentioned, it is a volume change, and therefore the structural integrity of the anode is being disturbed. But when CNT was added, and then the freestanding anode was cycled, that is this, like it gave a capacity, higher capacity of 450 milliampere hour per gram, and which is like almost stable. And even at the 100th cycle, at the current density of 200 milliampere per gram, we got a capacity of 443 milliampere hour per gram. Like for a normal graphite anode which is being commercially used, it is the maximum theoretical capacity is 372, and practically we get around 200, 250, like maximum 300. But here we can see that like we have achieved a capacity of 443 milliampere hour per gram. That is like above the capacity of the commercially used graphite anode. And even at higher current rates, like we have cycled it at 200 milliampere hour per gram, 500 up to 1 ampere and 1.2 ampere. It is showing like good capacities in comparison to the graphite anode. And then another material which we have worked is like with another metal, that is the SNO2 multi-wall carbon nanotube. And this was prepared using a refluxing process. Like on this, in this, like actually the carbon nanotube was coated with SNO2 particles, like as seen from the SEM diagram. Like these are the SNO2 particles. And with these, like we made the freestanding anode using the vacuum filtration technique. This is the freestanding anode, which is like highly flexible. And then we have made the lithium ion coin cell. This is the XRD of the samples, in which we can see the SNO2 peak and the carbon peak also. And this was around 30% loading. And then when we cycled, like an exciting phenomena was observed. That is like when we cycle the sample at 100 milliampere hour per gram, like the red line only shows the CNT samples. Like the CNT samples, like it gave a capacity of around 200 only maximum. And when the CNT SNO2 sample, that is our freestanding anode, was cycled, we could observe that the capacity is increasing upon the cycle. That means like, and then at 200 also the capacity is getting increased. And then it finally becomes stable. Like there is a capacity increase up to 500 milliampere hour per gram. And then after that it becomes stable. And then when this anode was again cycled at 500 milliampere hour per gram, that is higher rate capacity, it gave a capacity of stable capacity of 400 milliampere hour per gram for 100 cycles. And like then we investigated why this capacity is getting increased like during cycling. And what we could find is that during cycling, the carbon nanotube which was coated with SNO2, carbon nanotube which was coated with SNO2 is getting exfoliated. That means the carbon nanotube is getting opened, and it is getting converted into graphene nanosheets. Like you can see from these some diagrams, like it is getting disturbed, and then the graphene nanosheets are being formed. And then graphene nanosheets are being formed means there is a large number of space for the lithium ions to get inserted now. that means more number of lithium ions can be accommodated in the anode as compared to the previous condition, because like so many vacant spaces or active sites are being created. That is why the capacity is increasing. And once the capacity, once the disintegration is getting completely over, then the capacity becomes stable. That is here up to like around 110 cycles, the disintegration is getting over, and then the capacity becomes stable. So this is like another anode which we have worked. And another exciting anode which we have worked is a nickel oxide carbon nanotube composite. And the peculiarity of this anode material is that it can be prepared using a 5-minute combustion process. And because of this easy way of manufacturing this, it is it is industrially viable, and it can be used like as a future promising anode for the commercial lithium ion batteries. And like what we have prepared is the nickel nitride and multi-wall carbon nanotube was mixed in ethylene glycol, and it was heated in the oven for 5 minutes at 350 degrees Celsius. And then we got the nickel oxide carbon nanotube composites. And this is the SEM diagram for this, and we can see that the material is highly porous. That means there are porous, main porous sites. These are the active sites where lithium ions can get inserted. So from this porous structure, we can understand that there are a large number of sites where the lithium ions can get inserted. That means the storage capacity is being improved. And then finally, we did the cycling of this material in the lithium ion cells, and we could observe a capacity of 736 milliampere hour per gram at 50. That 736 means it is almost double the capacity of the commercially available lithium ion batteries. And this is with the nickel oxide carbon nanotube anode. And only when nickel oxide was cycled, we got a capacity around 382 milliampere hour per gram. This is mainly because of the volume change what is happening. But when the carbon nanotube was also added, the capacity improved up to 736. And this material was cycled at a very high current density up to 5 ampere hour per gram. And for that also it gave a capacity of 432 milliampere hour per gram, which is higher than the theoretical capacity of the commonly used graphite anode. And it has high reversibility even after cycling for higher rates. Then when again we reversed the current rate, its capacity is coming back to its original capacity. Therefore, it has high structural stability also. And we have the CSIR has recently transferred the technology of Indian lithium-ion batteries to the RASI Solar Energy Group for commercialization of this technology. And for that, we have a lithium-ion pilot plant at Chennai unit, and we are making 18650 and 18650 cells and pouch cells. And then we have made a pouch cell also with the nickel oxide freestanding anode, and that is Indian lithium ion battery. And then we have used our own cathode material, and the electrolyte material, everything is indigenous. And we have used the freestanding anode here. And from the comparison between the commercial lithium ion battery and the Indian lithium ion battery, we can see that there is a decrease in the weight of around 11 gram. And the contributing factor to this is the use of the freestanding anode, because the freestanding anode limits, there is no need of using the current collector, which adds the dead weight to the battery. And this technology has been transferred, as I already told. And then another material which we have worked is how to derive precious material or an anode material from a bio waste. And for this we have actually chosen the prawn shell waste. The prawn shell waste has been collected, and then we heated it at 300 degrees Celsius, and it was ground, and then it was alkali and acid washed, and then finally we got the carbon material from this, and that is a prawn shell derived carbon. And the structure of the prawn shell, when we derive the carbon, we could see that it is highly porous. We can see the pores here, and even it has a hierarchical porous structure. It has mesopores, micropores, and macropores also. It means that there is a lot of space for the lithium ions to get inserted, and therefore the capacity will be improved. This is the XRD. It has a turbostatic structure, that is an intermediate structure between the graphite and the amorphous. This is the graphitic peak, and there is an amorphous peak also. That is what is shown in this also. It has a layered structure but not properly oriented. And when this material was cycled, it gave a capacity of 740 milliampere hour per gram at a current density of 100 milliampere hour per gram, and when we cycle it at higher current density, it gave a 470 milliampere hour per gram. This is also very high capacity as compared to the commercially available graphite anode. And then when we cycle it at higher rates, then still it gave like high capacities, like around 202 milliampere hour per gram. So this is also a very good candidate, and then this is from the renewable energy resource, which is a bio waste. So like it is actually conversion of a bio waste into a wealthy material with high capacity which can be used. And the only limitation with this is like the yield is less, so we have to work upon how to improve the yield of this material. And so like the conclusion of my talk is that with the current like lithium ion battery technology, which is based on the graphite anode, it is impossible to achieve higher capacities, which is needed for electric vehicles and high-end applications like stationary energy storage. So we need to develop electrode materials which are which have high capacity and which is durable. And in this regard, like what I have shown is the work on like 3-4 different materials. One is antimony sulfide anode, which gave a capacity of 450 milliampere hour per gram. Then the SNO2, which gave a capacity of 500 milliampere hour per gram. And then the nickel oxide, which gave almost double the capacity of graphite, that is around 736. And then a prawn shell derived anode material, which gave a capacity of 740 milliampere hour per gram. And we have also transferred the technology for Indian lithium ion batteries. So we hope that in around 2 to 3 years, like we can have batteries of which are made in our country with our technology. And we all know that this year's Nobel Prize, 2019 Nobel Prize, was won for the work on lithium-ion batteries for the 3 eminent scientists. And as correctly said by the Royal Swedish Academy of Sciences, they have laid the foundation of a wireless, fossil fuel-free society and are of the greatest benefit to the humankind. And with due acknowledgement to its inventors, I end my presentation. Thank you. Hello? Hello? Am I audible? Hello?
Hello, am I audible? Ma'am, it seems
Yes.
there is some network issue at the organizer end. I think we should wait for them.
Yeah, yeah. Yeah, the,
Okay, okay.
yeah,
Was
yeah,
my
ma'am.
presentation
Yeah.
audible?
Yes, ma'am.
The participant
Okay.
can hear you very well.
It was a nice presentation,
Okay.
ma'am.
Nice.
Thank you. Any questions?
Ma'am, have you got any other patents also other than this work?
Yeah, actually we are filing a patent for the prawn shell derived carbon that is in process
Okay,
actually.
ma'am. Okay.
And for the freestanding anode, like Japan patent is also in process, and Indian patent is already granted.
Okay, ma'am. Okay.
Okay, it has been a wonderful presentation, ma'am.
Thank you. Any questions?
Compliment, take over to you.
Hello?
We can't hear organizer's voice.
Ranjita, ma'am, your speaker is turned off. Speaker is turned off.
Hello, am
Yes,
I audible?
audible.
Yeah. So,
Yes.
any of the participants, if are having questions to ask from Dr. Indu Elizabeth, they may ask. I think, madam, there is no question because I don't find. If we are having any questions regarding your presentation, we will email to you the questions, and thereafter you can revert back to them. Okay, ma'am.
Okay, okay.
Thank you so much. It was a wonderful pleasure to have you here. And thank you
Thank you.
once again, madam. Have a good day.
Okay, same to you.
Thank you, madam.
And thank you all for listening to me. Thank you.
Thank you, ma'am. So, our next speaker for the invited talk is Miss Nandini Sharma. She is from University of Delhi. Before she starts, I would just like to give you a brief introduction about her. Dr. Nandini Sharma has completed her doctoral degree from University of Delhi in the field of solar energy materials in the year 2018. He had delivered keynote talks and presentations in Oxford University and Surrey University, United Kingdom. She has received awards from international conferences for best research work and oral presentations. Being the reviewer of the international SCI journals, she possesses more than 4 years of teaching experience in the University of Delhi. She has published more than 10 research papers in reputed journals and has written a book on principles of nanotechnology of international repute. So it's my huge pleasure and honor to invite Dr. Nandini Sharma, working in Research Lab for Energy Systems, University of Delhi. And today her topic for discussion is characterization techniques for studying properties of nanomaterials. So may I call Dr. Nandini Sharma.
Hello.
Yes,
Hello.
yes,
Am I
Nandini.
audible?
Yes, yes.
Okay,
You
sir.
are audible and visual, both. Thank you.
Okay, thank you so much. Yeah.
Okay.
Good afternoon, everyone. Thank you so much, Nilesh sir, for inviting me to present a talk at such an international platform. And today I'm going to talk upon on the topic characterization technique for studying properties of nanomaterials. In the yesterday's lecture, we all saw that what is nanoparticle, anything which is ranging within the 100 nanometer range is termed as nanoparticle. And this picture is just showing how the nano can be compared to the material which are existing in environment, like football ranges in centimeter, our hair is in millimeter. And similar to that, nano is anything which is having the unit that is 10 to power minus 9 meters. These are different structures. They are showing the different dimensionality, the 0 dimensionality, 1 dimensionality, 2 and 3. In the further slide, we will discuss how the dimensionality changes and how the movement of charge carriers are getting affected with the dimensionality. He was a man, Dr. Richard Feynman, who said that there is a plenty of room at the bottom. This means a lot of applications can be deduced by using the nanoparticles, nanomaterials in all sets of fields. And even based on this, his thought, the STM was being invented in 1981, which led to the discovery of C60 fullerene. And the term nanotechnology was coined by a famous scientist, Norio Taniguchi, in 1974. This is how all started in the field of nanotechnology. Now, here we can see different sets of nanomaterials which are being classified based on their dimensionality. 3D is any material, like we can see all dimensions, like we have 3 axes, X, Y, and Z. All the 3 dimensions are not lying in the nano-dimensional range. So that's a bulk material. If any one of the dimension is lying within the nano range, then it's a 2D material. And if one of the dimension is lying in the nano range, then it's a one-dimensional material. Examples are nanorods, tubes, and fibers. And like in this particular presentation, you will see in further slides, I will be talking about the particular nanostructure, that's quantum dot, which is having a 0 dimensionality. This means all the 3 dimensions are being confined for the charge carrier, that electrons and holes. That's termed as 0 dimensionality for them. And because of these dimensionalities, 2D, 1D, and 0D, based on these dimensionalities, a wide range of applications can be assessed, and new things or devices can be introduced in the field of electronics or in the field of medical and various industries. So this is a 6th revolution which is introduced in the market. First for industrial, then comes the nuclear energy, silicon, green, and information in the 5th number. And after nanotechnology revolution, many things or many pathways were being opened for the researchers and scientists to explore. And this was being mentioned by D.L. and Bromley. Why we are actually focusing on nanoscale materials? Because many properties get enhanced, like catalytic. First of all, catalytic property gets enhanced because the higher to surface volume ratio is presented to the upcoming particle, and then the electrical properties can be modified based on the doping, or yeah, some materials in their pure form are also electrically conductive or resistive in nature, so their applications can be explored. Even in bulk material, the properties are there, but when we go towards the nanoscale, or we are reducing their size, their properties gets more and more enhanced, and that leads to a major difference when compared to the bulk material as compared to nanomaterial. And similarly, the magnetic, mechanical, optical, spherical, and biological properties are much more different as compared to the bulk material than to nanomaterials. That's why we are going towards exploring and synthesizing the nanoscale materials. Like we talked in the previous slide, that was based on from how many dimensions the particle is getting confined, and we could define them at. But here it's showing the dimensionality to be opposite. But we are talking in terms of from how many dimensions the charge carriers are getting quantized. Like we can see here, one-dimensional quantization. This means electrons can easily move in 2 dimensions, but in 1 dimension, its movement or its transportation is being prohibited or quantized. Based on that, different nanostructures can be formed, 1D, 2D, and 3D quantization. And then, as we talked earlier about the quantum dots, where all the 3-dimensional quantizers, electron can easily move in 0 dimension. This means there is, from all the 3 dimensions, its movement is prohibited. It actually it leads to the formation of discrete energy levels, like we used to talk in quantum mechanics as an application of particle in a 3D box. So that's actually the particle in a 3D box is directly depicts the application of quantum dot in various fields. These are the more nanostructures: nanorods, wire, tubes, flower, forest, graphene, quantum dot. I've highlighted quantum dot because I was representing how the quantum dot can be synthesized and how their properties were being assessed by using various characterization techniques. There are more nanostructures. These all are being formed by various scientific researchers: nails, stars, water, tetrapods, rings, combs, cubes. So we have multivariate synthesis routes, and along with that, characterization techniques are also available. But basically, I will be talking about the chemical synthesis route, that's a co-precipitation route. And for the characterization technique, we can use the structural and the optical, and for a surface area, BET is there. I will be talking in detail in the further slides. So basically, all characterization, all synthesis methods can be classified in 2 subtopics. That's a top-down approach, and other is bottom-up approach. If we go from bulk material, like from a bigger material towards a powder size and going to nanoparticle, or we're employing some physical method like R to discharge method or inert recondensation, milling or grinding the things, then it's termed as top-down approach, going from the higher size to a lower size. And for bottom approach, we are starting from at an atomic level, and the cluster formation occurs and then leads to the formation of nanoparticle. That's the bottom up approach. Normally, people are exploring the bottom up approach because it's having higher advantages, and cluster and agglomeration, aggregation is less in case of bottom approach as compared to top-down approach. And if we talk about the bottom approach, 2 methods are basically used: chemical method and biological method. Chemical method is common to both top-down and bottom approach, which includes a co-precipitation method, social, microemulsion, hydrothermal. All sets of methods are being comprised in the chemical method synthesis. Now, what properties we actually want to monitor while studying our nanomaterials? There are basically 2: physical properties and chemical properties. In physical properties, the size, shape, specific surface area, aspect ratio, depending on we are taking a rod, that is length is to width ratio, agglomeration, aggregation state, that corresponds to a higher content for defining its charge transportation rate, how efficiently the material is able to transported charge carriers. Size distribution. Size also affects directly the optical band gap and optical properties and electronic properties too. Surface morphology and topography, structure and solubility. And in chemical properties, we will be studying the composition and phase, what actually the crystal is, what is its structure, how is what is the composition, and which are actually the reactive sites which are contributing in a particular device formation. And based on hydrophilicity and lipophilicity, we can design further materials, or we can use them for an application like cell screening materials or water repellent materials. So based on these properties only, we can optimize it. By optimizing these properties only, we can make use of these nanoparticles to be used in further applications. So what actually is characterization? In this characterization, we will be studying all these properties, and that's determining its structure and properties and distribution of elements by using some kind of microscopy or diffraction technique, or either the atomic for microscopy, SEM10. So further, the main importance of these iteration technique is that we select and use the methods correctly and interpret the results according to the what is the principle of use of the particular technique. So by it will be used and analyzed in our accurate manner, and to know the understanding of the limits, what are the limit of different methods, and for and even one method is not very accurate in determining all the parameters, like XRD is being used to determine size, but still we confirm it using TEM because it is more accurate and it provides accurate information about the size of nanoparticle. So while studying the morphology, we are always focusing on the morphology, size, uniformity, structure, phase, specifics of the defects, common things, and when we go from using that powder for coating into a thin film, for transforming that powder into a thin film for different usages, like for designing a solar cell or light emitting diodes, then we are more interested in looking at its texture, morphology again, porosity of the film, film thickness, conductivity, stability, defects, transparency, fractal cracks, charge transfer resistance. So all these properties are playing very important role unless and until we are not clear about the prepared samples characteristics, then we cannot make its use in further applications. So basically we can classify the characterization technique in 4 parts: structural, optical, electrical, and magnetic. In structural morphology, and in defining the structure and morphology, we make use of scanning electron microscopy, SEM technique, and transmission electron microscopy, atomic force microscopy, and scanning tunneling microscopy. Basically, SEM is used to know the morphology of the material, and also to know SEM with EDAX, energy dispersive absorption X-ray spectroscopy, is being utilized for knowing its elemental composition, whether there is any extra impurity element or not. Then TEM, transmission electron microscopy, enables us to know the accurate size of the sample. Along with that, we have a spectrometer electron diffraction image, SAT image, by which we can know whether our material synthesized is crystalline in nature or amorphous in nature, and even if it's crystalline, that it's monocrystalline or polycrystalline in nature. So it enables us with so many uses. And then comes the AFM, atomic force microscopy. By this, we can know the thickness, and still by using the STM, we can know the thickness of the thin film synthesized, and also the roughness and smoothness of the sample coated can also be known by using AFM and STM techniques. For crystal structure, what is actually the crystal synthesized is, what is its identity? To know its whether it's a single phase or multi-phase, we make use of X-ray diffraction technique, Fourier transform infrared spectroscopy, and Raman spectroscopy to know what kind of bondings are being involved and how is like at what frequency are these elements vibrating. By this, we can know the elemental composition. Along with that, we can know the crystallinity and what is actually the identity of the atom. We can identity of the material synthesized. We can actually know. For optical property studies, we make use of photoluminescence, which helps in visualizing defect rates, near bandage emission, and also by using time-resolved photoluminescence, which is an advanced version of photoluminescence characteristic. It enables us to know the number of minority and majority carriers which are being involved in that sample. And ultraviolet visible spectroscopy is being performed prior to PL, just to know like what is the optical energy band gap and at what wavelength is the sample actually absorbing the things, and what is its this sample is transparent to what kind of or which range of wavelengths. So this is used for determining that particular thing. And similarly, Hall effect is widely used, and the 4-probe method is used to know the carrier concentration and mobility. That is to study the electrical properties of a material. I will be using an example from my work that I synthesized tin oxide quantum dots and how these characterization techniques were used to study the properties of these quantum dots. And then further, this material, the synthesized nanostructure of tin oxide, was being utilized to study its catalytic activity for degrading the eosin Y dye under the solar radiation. And I use normal direct sunlight for knowing its degradation rate. Co-precipitation route was being involved, where I use an anionic solution, cationic solution for a tin as a tin chloride was used for the precursor and lithium hydroxide was used for the cationic solution and these two were mixed in some appropriate amount, which I will discuss showing the next slide, and which leads to the nucleation and coarsening, and which leads and further the nucleation and large number of small particles are formed, and we can see these particles in the form of light yellowish froth formation at the top of the liquid, and then these are being filtered by using a filter paper, or either if one is having centrifugation machine, these particles centrifuge at a high RPM just to separate the particles from the liquid, other impurity atoms, and then these are dried in the oven and calcined or annealed at higher temperature to remove any impurity atom. So this is the actual or the detailed explanation of what molarity was being used for tin chloride dihydrate, and ethanol was used as a solvent for the tin chloride, and lithium hydroxide was taken 1 molar, which was being mixed in distilled water, and then these were slowly added by using a burette. And then these, after mixing it, was being more stirred for 1 hour for SNO2 quantum dots to nucleate. And then the residue obtained was, after washing, it was kept for drying in oven for 6 hours at 90 degrees Celsius. The main thing is that we anneal the prepared sample. After drying the sample, it was being grinded well by using pestle and mortar, and then it was annealed at different temperatures, at 5 different temperatures, which was termed as sample S1, S2, S3, S4, and S5. And based on the annealing temperature, how its structure and optical properties varied, and how it affected its application in photocatalysis, we will be discussing. And this then a photocatalytic activity test just involves by mixing the catalyst prepared, that is the SNO2 sample which was being prepared. Then after annealing it at 5 different temperatures, it was being mixed with the eosin Y dye solution, stirred for some time, and then it was being illuminated towards under direct sunlight and left by covering it by a Duracell under such that it does not get evaporates. So it was kept in the sunlight for a certain time duration, and after equal interval of time, the UV vis absorption spectroscopy was being taken to know what is the degradation rate of this sample towards the eosin Y dye. That's the eosin yellow organic dye molecule. How fastly this sample can degrade that dye molecule. So it was being studied to test its photocatalytic activity. This is the XRD pattern of S1, S2, S3, S4, S5 sample, and we can clearly see from these XRD peaks as the annealing temperature is increased, the amount of crystallinity is getting increased, the full width half maximum getting decreased. But here one can say that it's quite a resemblance, it's having a quite resemblance to a amorphous sample, but for knowing whether it's amorphous crystalline in nature, we further went with the TEM image along with the selective electron diffraction. And there we were able to see that it's actually a crystalline sample, and with the increase in temperature, the size is increasing, and it was termed as quantum dot, the 300 nanometer sample, because its size is in comparison with the Bohr exciton radius, and for tin oxide it's 2.7 nanometer, and lattice parameters were also observed to increase, and when the cell volume was being calculated, the volume was highest for S5 sample and lowest for the S1 sample. And all the peaks were matching well with the JSPDS file, which was being taken, like the card number is given. And this structure was being we have Topaz-P software at the University. I use that software to construct that structure, and the XRD parameters were being used for constructing this structure, tetragonal butyl structure of tin oxide. The other SEM images were not that much clear. They were showing a lot of agglomeration, and here we can see that particles are quite spherical, but as we increasing the but they are agglomerated, highly agglomerated spherical nanoparticles. We went for, but we can see from the EDAX images, there are compositions is comprising of tin and oxygen elements and not other elements. No impurity peak is rather than tin oxide elements. So we went with the high resolution TIM image. Here we can clearly see that the scale is 50 nanometer and here is 5 nanometer. The diffraction fringes can be seen, and diffraction occurs for the crystalline sample when, and by using these, the interplanar spacing were being calculated by using these particular pattern. And also for S3 sample, as the ending temperature was increased, we got to notice that the size was increasing. And here again, we can see the fringes which were being formed here. And from selected area electron diffraction, we determined the D spacing. And by calculating the D spacing from the center, we mentioned it at to the particular Miller indices corresponding to various back diffraction angles. So these results were corroborating well with the XRD results, and which confirmed that actually the quantum dots have formed, and these were having a size ranging to 5 point something nanometer, around 6 nanometer. This is for SO sample. Again, it was also, as we anneal the sample more, it was annealed, then it was found that again, the sample is crystalline in nature and size is increasing with increase in temperature. Then UV-based absorption spectra was being used to study its optical properties. These are the absorption spectra for various samples, and we use a TOC plot, that is by using this data only, this plot was being done to calculate its optical band gap energy. And by having a slope, by calculating its slope, the optical band gap was being calculated, and it was found out to be 4.1 for S1 sample, 3.8 for S2 sample, 3.7 for 8 for S3, and so on. And we got to observe that with the increase in ending temperature, the crystallite size was also increasing, but the band gap was found to decrease with the increase in ending temperature. So band gap and crystallite size are inversely related to each other. From there, we found out this thing. And this is actually due to the quantum confinement effect, that band gap is coming out to be very higher than the normal band gap of tin oxide. Then PL spectroscopy was being performed, and here we can see there is a catalysis activity. Further, the photocatalytic activity of all the samples were tested, and we were able to find that after 60 minutes of irradiation under normal sunlight, this red dot is showing that for S1 sample was actually able to degrade the dye to the maximum extent in comparison to other samples, and that was just due to its confinement effect and discrete energy levels which were being present in the S1 sample. And the size was quite lower, and lower size correspond to the higher specific surface area. And this is again showing, then we have used this data to calculate the rate constants for different samples, because the slope will get, because it's following the first order kinetics in the catalysis. And by calculating its slope, it will give the value, the slope will give the value of rate constant for different photocatalysts for S1, S2, S3, S4, S5 samples. And we can see the degradation of eosin while lowered for other samples due to growth of bigger particles and decreased oxygen content from their surface. So this is the complete result, that for S1 it's degraded up to 73% dye molecules or after 60 minutes of irradiation in normal sunlight. But for other, there are many more applications just now. By using, we are able to activate our nano catalyst, and then catalyst generates within the catalyst, the exciton pair gets generated at electron, then holes are created, which alters the chemical bonds, and excitation of semiconductor photocatalyst generate the exciton pair. And this exciton pair actually reacts with the eosin Y dye molecule. And why we are trying to degrade this dye molecule? Because it's highly emitted from industry as industrial waste, and this is also present in several river waters. So that's the main task, to clean these water bodies. It's energy saving because we are using natural biologically harmful, sustainable and because to carbon dioxide and water. Other applications are nanobots, but it's still in R&D phase, and one can use the nanobots which can use layer is getting thinned up. We can use these small microscopic materials to for preventing that ozone thinning, and it dimension micrometers, and its application are in drug delivery implementation. How it's used in drugs, because right now we are having for cancer treatment, we are using radiotherapies and chemotherapy. It's being researched nanorobots, which be specific towards active sites of the cancer cells, and it will release the medicine that will kill the tumor directly and side, not affecting the other cells inside the human body. They are even there's even a possibility that they will clear the blockage in the arteries very well, because the size is so small, targeted for nanoparticles. So it opens up a future for smaller, lighter, and powerful programmable nano devices and nanorobots programmed to attack or reconstruct the molecular structure of cancer cells and viruses, and slow reverse aging process and life expectancy. It can also help in removing the contaminants from water sources, as we talked about the photocatalysis process in our whole presentation, and even in cleaning up oil spills. So our dependence on renewable energy sources would diminish with nanotechnology. How it will diminish? Because by using this particular application, that is remove contaminants from water sources, again we are able to generate water and CO2 as a byproduct, and these water molecules can be used to produce the hydrogen energy, which will be acting as a fuel in the near future for our vehicles. The other various nanotechnology research centers available in India. I did my PhD from NSIT. It's a university now, and earlier it was under University of Delhi. And presently, I'm utilizing the UC University of Delhi Center for getting my things right and doing my research work. Thank you so much.
Now, any question?
Hello.
I think there is no question.
Okay.
So right now we are not available with any of the questions from our participants. Once we are having some questions, we will get back to you, Madam Nandini. Thank you so much for being with us. Now it's my pleasure to invite Dr. M.S. Michael, Associate Professor from the Department of Chemistry, SSN. I just want to give you a brief introduction about Dr. Michael. Dr. Michael received her PhD from Madurai Kamraj University for her work in electrodeposition at Central Electrochemical Research Institute in 1996. She did her postdoctoral research in the field of lithium batteries at Université Pierre at Marie Curie, Paris, University of Malaya, and Multimedia University, Malaysia. She joined SSNCE on her return from abroad and took up academic teaching and research in 2006. Currently, she is working as associate professor. She has published more than 40 research papers, edited a book, and earned 4 granted patents, 3 Indian and 1 Malaysian. She has completed 3 research projects funded by DST and DRDO. So it's my huge honor and privilege to invite Dr. M.S. Michael. And her topic for today's discussion is challenges in supercapacitors. Dr. M.S. Michael, please.
Yeah, Dr. Michael. Okay, your slide is visual. Hello, Dr. Michael. Please turn your phone speaker. Please turn your speaker. Your voice is not audible. Please, you are not audible. You are visual, but your slide is visual, but you are not audible. Please. Please turn your sound, please. Your voice is not audible, madam. Please. Hello. You are not audible. Yes. Please on your sound. Speaker, please.
And now we go back.
Yes. Now
Yeah.
you are. Yes.
Okay.
Yes. Okay.
Okay. I would like to thank the organizer for inviting me. So capacitor have been used for many purposes. So it can be used as a buffering one, that it can buffer that energy, or it can be used as a power assist, or like that it is going. You can see the space also. It can, in the renewable energy, it can use to store the energy along with. So it extends the life of that battery. So when you talk about all the applications of the supercapacitors, it is a power source. It cannot act as a standalone energy storage devices. It has to be combined with battery to improve its life. That is the main thing that's happening here. So this supercapacitor, as I mentioned, it is used in the electric vehicle also. Nowadays, they are going with the electric vehicle, sometimes a hybrid or purely electric vehicle. In that case, that power and all, during acceleration, the battery cannot support. So it is a power energy storage device. So we have to go with the battery, the capacitor, it has to be combined with. So it is like a battery. So it extends that life of battery. So besides that, it is another one important concept in EV is regenerative braking. What is it meant by? So during the braking system, all the energy is going as a waste. It can be stored by this super capacitor because of its quick charge and discharge characteristics. So what are the challenges in supercapacitor? As I mentioned, it cannot be used as a standalone energy source because its energy is much lower than the battery, but that capacitor power is also much lower than the capacitor, normal capacitors. It is in between. So this ultra capacitor or supercapacitor, ultra capacitor is another name for supercapacitor. It fills the gap between battery and the capacitor, normal capacitor. So if you want to improve that one, so we have to do some engineering in the electrode material. Not only electrode material, so many other challenges are there, but I am now going to concentrate only ESR. So we can see the sloping line. So ultra capacitor, it's so not so quick as normal capacitor, but it is better than this battery. So quick charge and quick discharge. That is the ideal for capturing that regenerative braking system, energy going as a waste during the regenerative braking in the electric vehicle. So now we can see what is capacitor. What are capacitor? So the normal capacitor, we know it consists of two plates. So conducting plates, it is filled with dielectric medium. So when you supply the current, the voltage, what will happen? This dielectric medium will polarize and it will give that charge separation will occur in the positive and negative side. But in the supercapacitor, we have the material, that carbon, especially carbon material. So with high porosity, in order to increase the surface area, it is connected with, it is coated on the current collector. So when you connect it and send polarize, and it is immersed in the electrolyte. So it's like that, it's immersed in the electrolyte and sending the voltage, polarizing. What will happen? So one electrode will carry positive charge, other electrode will carry the negative charge. Now, because of this charge, this positively charged electrode will attract the negatively charged ions. Similarly, negative charged electrode attracts the positive charge. So now we can see two capacitors will form. One this side, anode side, one other side. Two capacitors are formed. But here, that when you compare this capacitance of the normal capacitor, then here the capacitance is so high. So high means it is in hundreds of farad per gram. How it is occurring? How can we achieve this one? You can see here. So when you look at this normal capacitors, we can change only area, but we cannot change the D because it is due to dielectric medium. So we can see the area we can change or increase in the rolling type in order to increase the capacity. But here we can change or improve that capacitance by reducing the distance between the electrode and the electrolyte or the adsorbed ion, as well as the surface area of that electrode. So carbon material which is going to be used. So it is surface area, generally the carbon materials surface area higher than 1000 meters squared per gram is usually chosen. Thus, because of that one, this capacitance is 10,000 times higher than the normal capacitor. So it is known as ultra capacitor also. Similarly, when you look at this charge discharge curve of this one, so normal capacitors, it is in the exponential curve. Why it is exponential? Initially, for polarization of dielectric medium takes little time. So because of that one, it goes like this and it reaches the maximum. So similarly, discharging also, it comes like this, the slope in nature. But in the electrochemical capacitor, we can see here, so because it is because of electrochemical layer formation. Once you put the electrode, once you insert the electrode inside the electrolyte, so automatically, so instantaneously one double layer will form. So it is called electrochemical double layer or Helmholtz double layer. But when you supply the current, the charge separated at the surface will be keep on increasing until the charge is supplied or potential is applied. Then the discharging, all the things will come out. So this is the one, this is the way that capacitor will work. So we are sending the charge or current, or it is connected with external circuit. So voltage is applied. One is acting as a cathode, cation. So anions are coming and getting absorbed. Here cations are coming and absorbed. So the charge is getting tensed. That electrode surface is enriched with charge. So it is the charge separation will occur here. So when you disconnect or discharge, so everything will dissolve and it go back. So all the ions will go back to this bulk solution. So this is the way it happens. So there are two types of capacitor. So one is only that charge storage because of the separation of that charge at the interface. So the positive electrode, negative ions, negative electrode, positive ions. But in certain cases, what will happen? So ion will start transfer through. So electron transfer will occur. So this what will happen? That electron present in that that electron transfer occurs from this electrode to that inside. That is some reaction because of the redox reaction. It is a very, very fast, quick reaction. So its characteristics all similar to this where electrostatic separation occurring in that EDLC, pure electrostatic electrochemical double layer capacitor. So it occurs only a few nanometer. So then when you discharge, so again it go back without any change in the structure of the material. So it is because of the charge transfer occurring across the electrolyte interface, its energy density is much higher than that energy density we are achieving in the EDLC. But that in fact the pseudo capacitor, it's called pseudo capacitor. So because of Faraday reaction and this all the characteristics all similar to this one that they call pseudo capacitor. So the pseudo capacitors, it is electrochemical double layer is also there along with pseudo capacitor redox reaction is occurring. Because of that one, all pseudo capacitor consist of two parts. One is EDLC part, another one is PD, the pseudo capacitive part. So we have the redox peak according to the reaction occurring at the interface. So now we'll see that is the one. So as I mentioned, so this EDLC, so I'm going to concentrate only on EDLC. I'm not going to talk about this redox capacitor. So EDLC, it consists of two capacitors. When you calculate or determine the capacitance, it is that of the capacitance, specific capacitance of the single electrode. So that we can see that one. So along with, so for these ions coming and getting absorbed, there is a resistance. resistant part is that it plays an important role in determining the energy density and power density. So this is the P maximum theoretically we can calculate if you know the ESR value. So it is ESR. So this is the resistive part of the capacitor. So if you want to get more power, so more power density, how fast we can, power rate capability, we have to reduce ESR. So similarly, the energy density also, we put V squared, but V squared is nothing but, so maximum voltage we are supplying minus IR drop. This R drop is nothing but again ESR. So ESR is very, very important factor. It will determine the performance of the supercapacitor. So what is ESR now? So ESR is not a single resistance. It is a combination of or summation of so many parts. All the parts involved in creating that resistance. That is called. First we start with the cell. So external contact resistance, electrode collector contact, internal electrode resistance, internal interparticle contact resistance, electrolyte resistance, separator resistance. So many resistance will come. So when you take the impedance diagram, it is easily seen. So what are the resistance? It is there in the supercapacitor. In general, the ESR value is deduced from AC impedance measurement at 1 kilohertz. Fixed frequency we can calculate. So we can see the diagram of impedance plot, Nyquist plot. So imaginary versus real part. We can see this is the diagram. So this is the Warburg's curve. Then it is the electrochemical double layer capacitance. We can see if it is an ideal capacitor, only that solution resistance is there. Other resistance are nil or negligible. We can get, this is the resistance, it is displaced from the zero. This is the solution resistance, then Warburg, then it is the electrochemical resistance, like this one. So there is no this resistance due to other part except the electrolyte resistance. But in real case, we can see, so electrolyte resistance, one semicircle will come. We can see this semicircle is due to, so the semicircle is due to this electrode resistance, electrode interparticle resistance. All the electrolyte cannot reach that electrode, no connectivity. So poor electronic and ionic nature of the material. So many things come into the picture. So electrode resistance. So this resistance can be reduced if you want to have a perfect ideal this type of curve. So similarly, when you see this one, so that IR drop also can be reduced. So we can, whatever and a voltage is supplied, so that can be extracted. That same voltage that without IR drop, we can get the energy. That can be also achieved when the ESR is reduced minimum. So similarly, we can see that is that one we have done. So this, when you talk about different type of electrolyte, so we can go with aqueous. Nowadays, people are working on aqueous electrolyte. We have started this work in 2004. So with that, some conductive carbon. So this surface area is very less. Our curiosity, we started, we did some work. We can see that capacitance ESR is around 1.31 ohm, very high value because of the surface area is very, very less. So almost 17 meters squared per gram. So that we can see the IR drop. It is very, very high. So that all this one, it is getting charged up to 4.5 volt. And when we start this extracting all the energy, what happens? So it starts from almost in the high current rate, it is after around 3.9 volt only it gets charged. So the elapsed time we can get that energy. This is called elapsed time. So the energy, the time we can get that delivering the energy by the supercapacitor is very, very less because of the voltage drop. So it has to be rectified. So how can we do that? That is about this talk. So similarly, that this one, this ESR can be easily found, whether this capacitor contains that very negligible ESR or it is containing more ESR, that and all you can easily found from this cyclic voltammogram. So cyclic voltammogram, if it is an ideal one. So if it is an ideal one, we can get a perfect rectangular shape. So this is the one perfect rectangular shape without any this deviation. We can get that one. That means whatever current energy is stored at the electrolyte interface because of electrostatic charge separation, so can be extracted fully without any time delay. That is, you are charging now here. So when you want to discharge, so without any delay, that is called time constant, it will come out. So this is the ideal one. Sometime what will happen if you take the porous electrode, so this charge separation or this electrochemical double layer formation will take more time because all the electrolyte has to go inside, diffuse inside the pores. Because of that one, we can see slanting type of this rectangular, but the shape is still fine, but it is slanting. But if you come to the pseudo capacitor, we can see there is a time delay. You can see here. So this is the time delay. So when you charge it, when you discharge it, it will take its own time to come to that, this deliver the charge. So this is time delay. So it is because of ESR. It is very, very important because if you want to apply that supercapacitor for any pulse power, we expect that power, it has to be supplied at that time, instant time, but it won't occur if the ESR is very, very high. So this is our ideal capacitor. It has to be, it exhibit rectangular shape. Now we can see how can reduce that one. So with it is, if it is ideal capacitor, it must be rectangular shape. Sometimes, so it is our work. We just published in Carbon Letters. So we optimize that structure. We can optimize the structure, especially porosity of the carbon, in order to make it behave like ideal capacitor. So we have done this one. You can see here, this is the one condition. So we have optimized that chemical activating agent in this black pearl carbon. It is a commercially available carbon. We try to make it so electrochemical double layer material, so capacity material by chemical treatment. So we have optimized the chemical composition of this acid, that is boric acid. So we can see here certain concentration. So it is like a leaf shape. So it means, so we cannot get that all the energy stored. We cannot store the energy like normal one. Similarly, we cannot get all the energy stored at that without any delay. In fact, we cannot get all the energy. You can see it is going like this one. So at the moment of time, so if you want instantaneously all power, it is not at all possible. So that we have optimized the condition by using that diagram, that CA cyclic voltammogram. So we finally we have optimized the condition and we have published the paper as well. So this is the another one. So here it is with super material. So this is a carbon material with high surface area. So we optimize the condition in such a way that we can see, so the charging, so when we discharge it, when you switch over that one from charging to discharging without any delay, so there is no point in between. We can see it come to that same current. All the current can be extracted. So it is called ideal behavior. So this one we achieved by selection of the material. We have selected the material in such a way that it consists of the meso and microporous in proper ratio. So and proper alignment. It is very, very important. Synthesizing with this preparation of this hierarchical porous carbon is very, very easy. But it make it behave like ideal capacity. To show like ideal capacity behavior is very, very difficult. That is the one I am going to discuss now. So we can see here where we have chosen the material in such a way that it is alignment is really good. Similarly, we have done one more pre-treatment. So we reduce the electrode collector contact resistance. So there is always one resistance will come. So because we are taking the material in the solid form, so we have to coat it on one current collector, maybe in stainless steel or nickel. So we have to for the external circuit connection. So when it is not connected properly, there is a contact resistance. It has to be reduced. So this one we can reduce by pre-treatment. We have done some etching and everything. So we got that one like this. So this is, we got a perfect shape. So without any deviation, without any time delay, without any time constant. So we have patented already. So patent filed. So we are waiting for the examination of the patent. So the same thing. So this is a structure. We can see meso, micropole, all types of pore, all interconnected. Because of this one, the movement of ions inside the pores is very easy, accessible. All the pores area, porous volumes are accessible to that one. So we got that same ideal characteristics from that carbon. So we can see here also 45 degree and that electrochemical resistant tail. So without almost behave like ideal behavior. So this is another work. The same work in the 2004 we have done. So we can see it is a pseudo capacitor. That's why we can see here there is one time delay. So here it starts But so the voltage drop is also too high. So the time to extract all the power is energy is also getting delayed because of the nature of the material. So carbon is, we didn't select, so it's a curiosity, we started working with the conductive carbon working in the lithium ion batteries. So we have been working in lithium ion batteries also. So we studied that its EDLC characteristics. So now how can we reduce that ESR? By changing that porosity, by tailoring the porosity of the electrode material. It is very, very important. So we might think, so all the material, by increasing the surface area. So because according to that equation, so A is linearly proportional to the capacitance. Capacitance is directly proportional to the energy density. By increasing the area, surface area, we can increase the specific capacitance, but it is not the case. So many contradictory findings are reported. So no linear relationship between surface area and specific capacitance. Besides, so we can enhance the specific capacitance with the same surface area. We can enhance the specific capacitance as well as power density by tailoring the porous size, shape, and everything. So similarly, different size of pores ratio also play important role. So with hierarchical porous carbon exhibit better performance than of carbon with pores of uniform size and same area. So why it is happening? What are the reasons? So these are the plausible reasons we found. One is space confinement effect. Another one is overscreening effect and inaccessible pore volume. So other slides are about that, this effect only, explaining the effect only. When you talk about this mesopause, for example, that carbon material is containing mesopause. So mesopause can be any size between 2 to 15 nanometer. If the pore is little wider, so it can accommodate so these ions. So ions are always solvated. So then only it can move. Diffusion will occur. There is no ion-ion interaction. It can move easily. Diffusion is very easy. So it is coming and it is forming that layer. So it is the EDLC forming at the surface. So one side I am explaining. So because of this wide area or wider pore size, what will happen? So ions will come along with this solvated molecule. So not only one layer form both sides. So in between the ions are there. So what will happen? This ion, it is attracted because of the charge present here. So here it is, for example, it is a positive charge. So ions are negative charge. It is coming getting this. It is getting absorbed here. But what will happen? This counter ion will be here. So this will form another one. So next layer will form multi-layer. This is called multi-layer formation will occur. With this, because of occurrence, what will happen? So this one, the charge will be pulled towards the next layer. That is called counterbalance. It has to counterbalance that effect of pulling effect of the next layer. So because of that one, the ions are not dense. Besides, it is not so close to this electrode also. Now distance is also increasing. So charge density in that at the surface of the electrode is also increasing. So decreasing. Because of this one, what will happen? Capacitance finally decreasing. So if it is reduced this one, so we can increase that charge density, but diffusion rate will come down. So if we increase the energy density, charge separation, we increase the capacitance. But what about the power rate? So what is power rate? How can we make? If we want to diffuse or dissolve during the discharge, all the ions has to come out of this electrode and it has to move. So into the bulk. But if that amount of this solvent is very, very less inside, the diffusion rate will be easily affected. So if we make the pore size wider and wider, so power density will be higher, but energy, that capacitance will be lower. So there is a balancing thing must be there. So we have to balance that one. So now we come to the next one, micropores. If that's electrode containing only micropores. So micropores we can say, so some people are narrowing the micropores to that, this almost the diameter of the absorbed ion. So the absorbed ion, what will happen if it is very, very narrow? So if it is very, very narrow, it will allow only the ions to go in. So the solvent molecule cannot be accommodated. So it will come. So it come and get absorbed. So this side one layer, this one layer. Because of space confinement, there is no possibility of formation of second layer. So if there is no possibility of formation of second layer, what will happen? The energy density will be very, very high. So that capacitance will be increasing without any doubt. But next one, what will happen? So if it is only the ions are coming inside. So if it start moving, we can expect ion repulsion because all the ions are same charged. So what will happen here? So the ion can move here, but it cannot reach in the bottom. Here in the picture, I put all the ions are coming, reaching the bottom. But if that pores are very lengthy, so the movement will be rendered. It will be, so it's that other ions, adsorbed ions cannot, it won't allow the other ions to move inside and reach the bottom of the pores. So there is a strong ion-ion interaction, inter-ion interaction will be there. So the energy density also, if it is pores, nanopores with very short length, so it can be fully, that layer can be formed inside the pores fully. But if it is very lengthy one, there is no possibility, there is no accessibility for the ions to go inside because of there is the diffusion path is not there, that is electrolyte is not there, besides that ion-ion interaction. So capacitance may increase, but that power rate capability is very less. Power will be reducing because when you discharge it, how can the ion can come out? There is no electrolyte, how can it come out? So it is the problem. So what is the solution for this one? So we can go with hierarchical porosity carbon. Porosity carbon. So the hierarchical porosity carbon. So we have to have that ratio of this meso and micropores. So that is not only the sole criteria for increasing this power density. Its alignment is also very, very important. So because it must be interconnected. For example, one narrow pores, as I shown that picture in the previous slides. So it must be interconnected. Narrow pores, micropores, mesopores, it must be interconnected. So what will happen? Micropores enrich the energy density, that is the ions are going inside the micropores and it is getting formed that electrochemical double layer. Why? That diffusion of ions can be facilitated by that electrolyte present in the mesopores. Like that it has to go. So the arrangement of pores with accessible inner pores reduces the distributed ohmic resistance associated with the dead site. Otherwise, this surface area will be less. So whatever surface area we are calculating according to that method, whatever method available, so it must be higher. But that what is the effective surface area? They call it as effective surface area will be lesser than this one because all the sites are not available for the formation of electrochemical double layer. So this is the recent work we have done and recently published carbon letters. This is the one. So here that one. So it is done by these engineering students. So we found one material. So that is nothing but carbon black paint pigment. So the paint pigment, we got that pigment from one company. So that conductivity is really good. So we thought, why can't we use it as a electrode for EDLC? So we have, because that the pigment is already coated with, it is treated. So we want to clean it. And we, as the same time, we want to activate it. So we have done with boric acid. So during the boric acid activation, we found the generation of micropores at the surface of the nanoparticles. Besides, so one important unique nature of this nanoparticle is agglomeration because they cannot stay as nanoparticle alone single. So it will be agglomerated coalescence of nanoparticle because of this intrinsic surface energy. They come together, they form so many agglomerates. So, but inside the agglomerate, we can see so many voids are there. But the voids act like meso and micropores, facilitating the diffusion of ions. So this is the one. So we can see here. So this is the way it happens. So this is that our result. So we have got the STEM micrograph of this one. We can see these are the agglomerated particles with pores, micro, meso, pores, everything. It is coming inside. Even macropores are also there. So we can see all the things. So because of this pores or voids, all that diffusion of electrolyte as well as ions are facilitated. It is easily going. The power density is really high when you compare to that particle carbon material with the same surface, same area, same surface area. So we compared here. So in the aqueous electrolyte, its behavior is very, very high, but non-aqueous electrolyte, because of ESR maybe, so it is little lower. But we can see initial before this activation as a supplied material as a pigment for paint. So we can see it is, yeah, even it is a rectangular shape, but that capacitance is very, very low, but by increase, so that capacitance enhanced very much. Similarly, power and another one. So from my discussion and all the points, so it's very clear ESR is very, very important because supercapacitor are the power source. So it is not an energy source. So it can go along with any energy storage devices, or it can act as a buffer, or it can act as a power assist. It's a backup power, like that it can use. So that for power source, the very important thing is power rate. That is, it has, so under pulse power loads, how much energy it is stored can be delivered. That is very, very important. So this is the one. So ESR plays a very, very crucial role. So if it is ESR is very high, or what will happen? So the time delay will be there. So all the power which stored cannot be recovered. So delivered at the time, that time when it requires. So it is that ESR is that cumulative resistance. So different parts of capacitor. If you start from the current collector, going to the contact resistance, internal resistance of the electrode material, then it comes to this conductivity of the electrolyte, then it comes to the separator. So both sides, so it is a combination series of two capacitors. So all together it will have to double 2 times, it will come to whether it is coming. So how can we reduce it? How can we change it? We can reduce it. We can reduce this one. So we can play a role. So we can reduce this one by tuning that electrode also. So we can go with the hierarchical porous carbon, but hierarchical porous carbon as such cannot be this, it is successful in enhancing the power, specific power. So we have to tune the structure in such a way that all it has to create the pores of different sizes, meso and micro pores. They all must be interconnected. It is very, very important. So interconnected pores and controlled porous structure facilitate rapid ionic movement. Otherwise, what will happen? It consists of only narrow pores, that nanopores or micropores of very, very close to the diameter of that ion. So there is no diffusion, there is no movement. Capacitance may be high, but the power density is very, very low. But if it contains only mesopores, there is also the problem. So energy density is very low because that cannot, this capacitance is very, very low, it will come. So when you contain both at different, it is not aligned properly. Somewhere the micropore is there, somewhere the mesopore is there. There is no connectivity, then also it is not useful of synthesizing hierarchical porous carbon. So that's why they are going with the template method. They are taking template, they are preparing that meso and replicating. So that replicating same meso and microporous structure, that is really, really useful. So arrangements of pores with accessible inner pores reduces the distributed formic resistance associated with the dead sites. So if the dead sites are removed, means all the pores volume is available for this EDLC formation. So all that electrolyte diffuse inside. So surface area will be equivalent to effective surface area. So surface area is totally different. It must be the effective surface area is the area which is accessible to the electrolyte or the absorption of ions. So it must be higher. So although it is easy to synthesize hierarchical porous carbon, optimizing the appropriate pore size and distribution with specific characteristics still remain as a challenge. So this is a challenge now. So if you want to reduce the ESR by hierarchical porous carbon, we have to concentrate on meso and micropores as well as its alignment. It is very, very important. So this is that summary of my talk. So thanks for your attention. So any question? So if you want, you can talk.
Any question?
Any questions?
Okay, thank you, ma'am. There is no questions.
Yeah, no problem, sir.
I over to Dr. Lovely Ranjita.
Okay, thank you, sir.
Thank you, sir. Thank you so much, madam, for being with us. And
Okay.
it was wonderful pleasure to have you here. Thank you, ma'am.
Okay.
Thank you so much.
Thank you. Thank you.
Now, the session for expert talk will start. And this session is chaired by Dr. Alka Dubey. Dr. Alka Dubey has completed her PhD at a very early age. At 27 years, she had done her PhD from Dr. H.S. Gaur Sagar University. She is the former principal of Athena Institute of Science and Technology. She has published more than 50 research papers in reputed journals and has been serving as an editorial board member of the institute. So for this expert talk, I would like to invite Dr. Alka Dubey from Athena Institute of Science and Technology, Sagar, Madhya Pradesh. Over to Dr. Alka Dubey.
Madam, please, you are not audible. Yes,
Good
okay.
afternoon, everyone. Hello. Am I hearable? Yeah, ma'am.
Yeah.
Good afternoon, everyone. Thank you for giving the session as a chance. So, this was a good session. The different kind of experts representing their speeches. So in that series, I want to just introduce Mr. B.C. Chanel, the first candidate in this session. Mr. B.C. Chanel has completed his PhD at the age of 26 from Kumaon University, Almora, Uttarakhand. His research area is induced at high energy particle physics, mathematical and theoretical physics, etc. At present, he is assistant professor in physics at G.B. Pant University, Pantnagar, Uttarakhand. He has published one book and more than 40 papers in reputed journal and has been serving as an editorial board member of reputed. So I want to invite him for his topic, spontaneous space-time algebra, a powerful tool for relative quantized electromagnetic field. Welcome, Mr. B.C. Chanel, and all the rest for your presentations.
Thank you. Thank you. Thank you, Dr. Nilesh Rayan. I'm audible?
Yeah, you audible and visual both. No issue. You are audible, sir.
Yes, sir. Thank you.
Yes.
My screen is visible or not?
Yes.
Okay, thank you so much. So, myself, Dr. B.C. Chanel, from the Department of the Physics, G.B. Pant University of Agriculture and the Technology, Pantnagar, Uttarakhand. And the topic of my talk is the quaternions space-time algebra, a powerful tool for the relativistic quantized electromagnetic field. So, these are the outlines of my talk. The first one is the general introductions, where we discuss about the classical electrodynamics, magnetic monopole, quaternionic quantum electrodynamics, quantized electromagnetics, wave propagations, and finally the result and the conclusions. So first we come to the introductions. So the classical theory is, of course, the Newton's law of the universal gravitation, the physical field theory that the classical nature may be called the classical field theory. But in 1873, J.C. Maxwell, in one of his fundamental work on the electromagnetism, unify electric field in a quantum is nothing more but linear algebra are void. So that means we require the symmetry in this Maxwell equations. So the asymmetry of the Maxwell equation require the existence of the magnetic monopoles. Dirac put forward an idea of the magnetic monopoles as generalizations of the electrodynamics. E and the magnetic monopole G is equal to half n, where n is considered the quantum numbers, where the value of the n is equal to 1, 2, 3, and so on. The magnetic monopole dions were first proposed by the Julian Swinger in 19. He discovered and they analyze the behavior or the dions. In 1873, Dirac symmetrized Maxwell equations with monopole called GDM. I mean the generalized Dirac-Maxwell equation. If monopole carries electric charge in addition to the magnetic charge, that means it is called a dion. So the definition of the dion is the dion has not only the electric charge but also the magnetic charge. Consider the Euclidean structures and the phenomena for the case of the dion. So let us start with the 4 vector representations that components. If we check the, it is world vector x, it is board x is equal to, it is x, y, z are called the space coordinate, and the time coordinate included the imaginary units minus I. So here we see this is the Euclidean structure. It is plus, 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 and the minus. So similarly, equation number 3, we can write the 4 gradient for momentum, electric for potential, magnetic for potential, electric for current, and the magnetic for current in terms of the Euclidean structure, where the last 4th terms is purely the imaginary unit. So what is the generalized Dirac-Maxwell equations? If we consider the magnetic monopoles, so we may write the symmetrical form of the Dirac-Maxwell equations. It is called the generalized form of the Dirac-Maxwell equation, GDM equation, for the case of the dions. Here we check the del dot S is not equal to 0, but it has some value and it's depend the magnetic charge density. So these equations are well invariant now under the duality transformations. We also may write the following quantity. These are the complex quantity, their real and the imaginary parts as a electric and the magnetic constitute of the dions. Where if we check the equation number the 11, the generalized dynamic charge can be written in the form of E plus Ig. E is called the electric charge, G is called the magnetic charge of the magnetic monopoles. So similarly, we can write the generalized dynamic potential in terms of the A nu plus IB nu, and the generalized Dirac the dynamic current in terms of the J nu plus I K nu. So the question is, what about the generalized field of the dions? How we can show the generalized electromagnetic field in case of the dion? So if we check the duality invariance for the case of the GDM equation, we may write the electric and the magnetic field of the dions in terms of the 2, 4 potential A and the B in terms of the symmetrical manners, where A is the electric fields of the dione and B is the magnetic field of the dione. And if we combine these two, we get a generalized field for the case of the diones. Now, if we substitute these two equations in the GDM equation, we get the two set of the four vector and the scalar potentials field, given equation number 14, and the first part of the equation number 14 is represented the vector potential field, and the last section of this equation represented the scalar potential field, where the L1 and the L2 represent the relativistic Lorentz gauge conditions for electric and the magnetic charge of the dione, given by the equation number 50. So to develop the quantum mechanics and explain the quantized electrodynamics, we require some mathematical models and the mathematical algebra. So now we introduce the norm division algebra. A norm division algebra A is a division algebra over the real or the complex number, which is also a norm vector space satisfy the conditions norm of the x, y is equal to this much. So according to the celebrated Hooke's theorem, there exists four norm division algebra. First one is the real numbers, denoted by the capital R's. Next, C is called the complex numbers, Q for the quaternionic numbers, and O for the octonion number. But here we explain only the quaternionic algebra. So there are two theorems about the division algebra. Theorem first, real complex quaternion and the octonions are the only norm division algebra. And the theorem number 2 explain all the four algebra are the alternative division algebra. So how we can go from the real to the quaternion and the octonions? So if we check the Cayley-Dixon constructions, so real is R means the real, it's a commutative associative algebra. But if we go from the real to the complex, C, so C is non-real, but commutative and the associative algebra. And if we go from the complex to the quaternion, Q is non-real, non-commutative, but associative property is there. But if we go from the quaternion to octonions, it is the highest division algebra. It is non-real, but it follows the alternative rules. So in my talk, we explain the quaternions and the quantized form of the quaternionic electrodynamics. So basically, the quaternions represent the natural extension of the complex algebra and form an algebra under additions and the multiplication. Here, the units vectors, call the unit elements of the quaternions defined by the E0, E1, E2, and the E3 satisfy the following multiplications rule given by the equation number 60. These are the commutative, anti-commutative, and the associative rules for the quaternionic algebra. Here we use the del AV, it is a delta symbol, and FABC is a Levi-Civita 3 index symbols. So quaternionic quantum mechanics, how we develop. For the foundation of the quantum mechanics, simply we can start from the quaternionic wave function psi, and the momentum P can be represented by the equation 17 and the equation 18. The equation 17 represent the four wave function in terms of the quaternionic form. It is a pure quaternionic form it is vector algebra, and it follows the scalar algebra. So that means the quaternionic form can be represented the unified version of the vector as well as the scalar field. So these two equations, if you multiply these two equations in terms of the equation number 19 given by p psi equal to the m naught c psi, it is generally a quaternionic multiplication between these two quaternionic variables, and this equation generally defines the eigenvalue problems. It is similarly a p psi equal to lambda psi types equations. The above equation excavate the well-known Dirac equations of massive diodes, where we use the four-dimensional quaternionic momentum operators given by the P is equal to I h cross gamma mu del mu. So this equation is simply a Dirac equation for the massive diodes. So quaternionic quantum field equations. So using the quaternionic multiplication given by this equation, we get the following equations in terms of the quaternionic form. The equation number 20 to 22 called the quaternionic quantum field equation. It is first order field equations where we use the momentum and the energy operators. P is equal to minus I cross Nebula operators, and the energy E is equal to I cross del over del T. So we may also place the second order differential equation if we operate the Nebula operator both sides on equation 20 to 21 and the 22. So the equation 23 indicated the second order differential equations. These equations are very useful in electrodynamics as well as the hydrodynamics. It is a second order differential equations. It behave like as a wave equations. So next slide we can explain how this equation number 23 behave like as a quantum wave equations. So if we unify the scalar and the vector field in a single equation, so we can write the equation number 24. This is a quaternionic quantum wave equation. The additional terms 2 m naught h cross del psi upon del t describe the time dependent source called the damping terms. It is a damping terms resulting from the inertia of the massive particles, where the m naught is a relativistic rest mass of the particles. Therefore, the quantization conditions become the del upon del tau goes to this much, where the del t is equal to h cross upon m naught c square. This must be equal to h cross upon the change of the kinetic energy, delta ek. So here the tau is a classical time coordinates. Now, in view of the physical significance of the generalized quantum wave equation, we may consider the general plane wave solution of the equation number 24. If the psi is a plane wave equations and put this psi wave equation in the equation 24, we get the group velocity as well as the phase velocity for the case of the dyons. The quaternionic quantum electrodynamics. Now we may compare the classical electromagnetic equations given by the equation number 14 and the quantum equations is given by the equation number 24. So finally, if we compare these two equations, we get the interesting results. These are the novel results, where L1, L2 are the Lorentz gauge conditions, can be written in a quantum form like the equation number 31 and the 32. And the another important equations given by the equation 33 and the 34. Here we check the current density is directly proportional to the electric potentials, and the magnetic charge density K vectors depend the magnetic potentials of the magnetic monopoles. So the quaternionic quantum wave equation for the dual scalar potentials, we have the two scalar potential phi E and phi M of the diodes can be written the equation number 35 and the 36, where the electric charge density can be written in terms of the electric potentials and the magnetic charge density can be written in terms of the magnetic potential in equation number 37. So on the other hand, the quantized Lorentz gauge conditions for electric and the magnetic potential can be modified in the given equation del dot E equal to this much and the del dot B equal to this much. So quaternionic quantized Dirac-Maxwell equation, finally we found the quaternionic quantized Dirac-Maxwell equation given by the equation 38 to 41. These are the quantum equations for a quantum particles dione. The interesting part of these equations is that these equations are invariant under the duality transformation. If we check the validity of these equations, we have to check the duality transformations, the Lorentz transformation, CPT transformations, and if all the transformations are valid for these equations, so we can easily say these equations are the quantized equations for the quaternionic case. So if the relativistic mass m0 tends to 0, let we consider the stationary photons. So the quantized GDM equation can be converted the equation number 42. It is well-known equations called the Maxwell equations for the macroscopic particles, and we also call these equations can be used for the massless dions in a free space. So quaternionic quantized continuity equation, if J is equal to 2m0 upon h cross, it is a quantity depend to the mass of the particles, then we establish the generalized continuity equation for the massive diode. This is the generalized continuity equations given by the equation 43 and the 44, where the additional terms visualized. The third terms is the additional terms, J terms, visualize the torque density result from the two spin states, the quantum spin state of the diodes. And these two terms are also given by the tau E and the tau M. And if producing a polarizations PS given by in terms of the torque, continuity equations can be transformed in the equation 45 and 46, where we use the effective and the K vector effective are the effective dual current for the case of the dione in quantum state. Any question regarding my presentation?
I think there's no question. If anybody has no further kind of questions, please drop them inside the chat box. So I think this lovely, we shall call to the next participant. Shall we call for the next participant?
Yes, ma'am. Sure.
Now, the next one is Dr. Deepak Ashok. Dr. Deepak Jadhav has completed PhD from IIT Kharagpur in 2017 and MTech in 2012. This is at PU Berlin, Germany. He has published more than 20 papers in reputed journals with high impact factor and has been serving as an editorial board member of reputed journals. He has received Young Scientist Award at Rashtrapati Bhavan in 2015, 2018 and Swachh Award and Section Award from Ministry of DWS POI in 2017. He has received silver medal at IIT Kharagpur for PG studies and the design concept of bioelectric toilets. He presented research work at international conferences at China, Sri Lanka, Germany, reviewed several international projects on microbial fuel cells. So now next is Mr. Deepak Ashok Jadhav. We are inviting him for his title On-Site Application of Microbial Fuel Cells, MFC, for sanitation and scaling up challenges. Welcome, Dr. Deepak Ashok Jadhav. Good luck for your presentation.
Thank you, madam. Nice introduction. Is it audible?
Yeah.
And the presentation is also visible, right?
Yes, Deepak Jadhav. Continue.
Today, I am going to talk on different aspects apart from this physics talk, to deal with how this microbial fuel cell can be applicable for on-site applications for sanitation and what are the challenges we have faced during scaling up. This is the work that is conducted at IIT Kharagpur during my PhD research, and I'm going to discuss on this. So basically start with what is microbial fuel cell. It's abbreviated as MFC. So MFC is nothing but it's a two-chamber fuel cells. One is anodic chamber and another is cathodic chamber, where in anodic chamber it is totally anaerobic conditions where actually microbes are filled. It is fed with wastewater, anode electrode is provided, and in another compartment it is a cathode chamber where actual oxygen is supplied as a cathodic terminal electron acceptors. During this anodic oxidation, the bacteria that oxidizes the organic carbon from wastewater that releases electrons and protons. Electrons pass through this electronic circuit and captured at load or in case any electronic appliances, and whatever the protons, they are migrated through this proton exchange membrane. This further get reduced in cathodic chamber to form water, and simultaneously we can get electricity as in terms of electrical output to operate different electronic appliances as well as to charge mobile phone batteries as well as other applications. So here the major role is from bacteria, from wastewater, as well as different operating conditions and design aspect of microbial fuel cell reactor is an important aspect for getting higher output from microbial fuel cells in terms of wastewater treatment efficiency as well as power generation efficiency. So the application, it can be applied for wastewater treatment. It can be useful for energy recovery from waste. It can be used as a biosensor applications. It can be used as a byproduct recovery options, or it can be used as an external power source. Each system has its own limitations, as it has a limited lower power output and has some different scaling up constraint and cost issues. So these are the different components of this microbial fuel cell: anode, cathode. It has a membrane separator, wastewater, inoculum, cathode, as well as different set of catalysts to enhance or to mediate the rate of reactions, as well as different electronic circuits are needed so that it can be captured maximum charge from this fuel cell. So it has a it can treat a simple substrate like your acetate, glucose, as well as it can be treat a complex substrate, industrial wastewater, as well as waste generated from humans as well. So different kinds of microbes that with electrogenic microbes as well as some mixed inoculum can be used as a source of bacteria in microbial fuel cells for oxidation purposes. So let me come to the topic like why this need of human waste treatment. So considering the daily each minute almost 1.1 million of liter can be dumped into the Ganges river, and if we generate human waste, it contains almost 60 to 80 grams of COD, which can be a valuable energy source for this microbial oxidation purposes. And even when we directly dispose this human waste into the any water bodies without any treatment, it causes environmental pollution, and also it can contaminate the water as well as soil. And even this open disposal in many parts of rural India, it can lead to the transmission of many diseases. When we are comparing with conventional existing wastewater treatment system or our conventional septic tank system, it has a low efficiency, almost 30 to 40%. So almost like in normal septic tank, we are almost losing almost 60% of organic carbon into the drainage system. So we have to think about effective and efficient engineering design of this septic tank system, and this microbial fuel cell option that can be a sustainable and effective solution for such approaches. And this work has been published in Renewable Sustainable Energy Reviews in 2007. So the author is like we can couple or we can integrate microbial fuel cell system with our conventional septic tank systems, or we can modify the septic tank system with microbial fuel cells. So coming to the past literature, previous system literature, they have used human urine. Actually, human urine is a rich source of nitrogen as well as other minerals and carbon, organic carbon as well. So to harvest energy from this yellow gold, they have used this microbial fuel cell concept to charge mobile phone batteries when they have connected number of premises together. So similar work has been published in Energy Journal by testing with cow urine as a yellow gold in microbial fuel cells. So coming to the human waste, previously designed from a green laboratory in Ghana. So they have just coupled this microbial fuel cell with nitrification chamber. You can see as a yellow chamber as nitrification, and they have coupled it with normal conventional septic tank system. So in this case, they have obtained little less power. It's in microwatt. So we have worked with similar concept, and we are targeted to remove ammonia, as well as we have used different inoculum culture percentage to deal with this microbial fuel cells, and this has been published in some international journals. So we have come with concept of bio toilet. It is far away from normal bio toilet system that has been established in Indian Railways. So we have taken limitations of our existing conventional septic tank system has a limitation that it can treat almost 30 to 40% of organic carbon or wastewater. So we are almost remaining with 60% of organic carbon that has been directly disposed into the sewer system. So we have come with biotic toilet system or septic tank MFC to harvest the energy from this black water and sludge settle in the tank using microwave fuel cell for human waste treatment. So considering the energy value, this human waste can generate almost 14.7 kilojoule per gram of COD. And when we are capable to harvest energy from such energy-rich human waste, so it can be capable to harvest energy up to the 100 watts, which can be sufficient for lighting the small LED bulbs. So the suggested option biotic toilet system can provide a solution to generate on-site electricity. It also provides a solution for disinfection along with organic matter removed from human waste for rural part of India. This is the basic sketch or basic conceptual diagram about biotic toilet system for wastewater treatment and electricity generation. So, what are the human waste that has been received from this toilet that has been fed to the anaerobic chamber? So what are the bacteria fed in anaerobic chamber that oxidize this organic matter or organic carbon and release electrons and protons? These electrons can be harvested through PMS, that is power management system, where it can be utilized to illuminate the LED bulbs. It can be utilized for harvesting energy and can be capable to charge our mobile phone batteries, as well as it can be used for to operate different electronic appliances. After the treatment, almost like in such cases, we can get about 80 to 90% of COD removed in terms of chemical oxygen demand. So, and what is the remaining organic matter available? It can be further sent to the cathodic chamber, where we have provided sodium hypochlorite as disinfectant agent. So this disinfection will what are the pathogens available in anaerobic chamber after human waste treatment. So what are the treated effluent we get after cathodic chamber? We can use that treated effluent for reuse purposes, for flushing purposes, and for other gardening purposes as well. So this such biotic toilet concept is a novel application of microwave fuel cell into the septic tank, where we can remove the organic carbon, we can treat the wastewater, as well as we can remove the pollutants such as nitrogen, phosphorus, as well as additionally it can disinfect the anaerobic effluent, and we can use the treated water for further applications such as flushing as well as other applications. And we are published with Biosource Technology Journal in 2014. So considering this aspect, when we are targeted for field skill applications or practical applications for on-site wastewater treatment, we have come up with design constraints. We have modified the system with optimizing the operating conditions as well as parameters. We have checked the feasibility as well as scaling up issues of these microwave fuel cells, and finally, we have compared the economic analysis with existing conventional wastewater treatment systems, so we can overcome the challenges of scaling up of microwave fuel cells. These are some large-scale study or benchtop models that we have tested in our lab at IIT Kharagpur. So we have started with microliters to milliliters, and further we have scaled up the systems. Initially, we have tested different operating conditions for microwave fuel cells so that we can get optimized conditions for enhancing the power output from these microwave fuel cells. So initially we have tested the hypochlorite dosing. We have optimized the concentration of bacteria. Also, we have tested different sets of catalysts, cathode catalysts, as well as anode catalysts in microbial fuel cells, so that we can get the maximum output. And also, we have worked with modifications of membrane, so that we can find alternative, cheap, low-cost solution for this expensive microbial fuel cells. So, after completing the work with lab scale, we moved further for scaling up studies at IIT Kharagpur, which is a center of bioenergy. We came with our scale-up model of 100-liter capacity. So it is nothing but it's combination of single-chambered MFC as well as dual-chambered MFC, where we have used 36 different units of microbial fuel cells with using different catalysts as well as with different hypochlorite dosing. Further, we have combined 36 units into the stack arrangement, either in series connection or in parallel connections, and we have harvested the energy from such human waste. So such paper has been, we have worked with catalyst, and this paper has been published in Biosource Technology. So it has the different components where we have tested different catalysts with different analytic sludge treatment, and we have finally worked with power management system for harvesting the maximum current from such systems. We have carried out different analysis, routine analysis to check performance of all these 36 states of microbial fuel cells. So further, whatever the electricity generated, we have further amplified with power management systems, and this amplified power can be capable to charge our mobile phone batteries. In last three, we can see the application space. It can capable to illuminate small 10 LED bulbs. Also, it can operate light detecting sensors based on photo sensors, and it can capable to operate electric fans. So this is just a success story with our 100 model with the capacity where we can harvest higher current as well as with lower internal resistance, and the system can be capable to harvest Coulombic efficiency up to 5.6% when we have treated anodic sludge with alkyl treatment, and additionally we have provided with sodium hypochlorite as cathodic terminal electron acceptor for treating anodic effluent. We have carried out all these electrochemical analysis like impedance analysis, cyclic voltammetry analysis to find out how Coulombic efficiency can be enhanced with providing different treatment to the anodic sludge, so that we can harvest maximum redox current from microbial fuel cells. These are the power management system where we work with amplifying the power output from MFC when it is with stack arrangement. So we have come with results that this biotic toilet system can be a sustainable and renewable option to generate on-site electricity from human waste. It can, whatever the 100-liter capacity reactor we have designed, with, it has a low internal resistance with higher power output, and in this case we have used low cost ceramic membrane, which can be options for alternatives to the costly membrane. And also we have come with engineering and cost analysis for this model, which shows that the scalable MFC can be suitable for field applications when we are capable to harvest Coulombic efficiency more than 6%, and this can be a suitable option for on-site treatment of human waste. So coming with results of our 100-liter capacity reactor, we further go for field applications of this biotic toilet at IIT Kharagpur. So we have designed the system of 1.5 cubic meter capacity, that is 1,500 liters capacity of MFC, which treating the human waste from septic tank. That septic tank we have called as Sanjeevani, the short form of Swachhataga Jivan Savarna Evam Vidyut Nirmiti, that Sanjeevani toilets or the waste generated from the Sanjeevani toilets can be fed to the 1.5 cubic meter capacity microbial fuel cell. It has a design like six chamber compartment design, and the treated effluent can be finally supplied to the anodic cathodic chamber fed with sodium hydroxide and electronic cathodic electron acceptors. Such treatment work has been published in bioresource technology with alcohol treatments. These are the reactor where we are working with aggregating as well as installing our reactors with our team. So when considering its design, we have chosen carbon field as the electrode material. We have tested different anode catalysts as well as cathode catalysts for this microbial fuel cells, and we have worked on development of advanced power management system, and we have carried out electrochemical analysis as well as water quality analysis. So this MFC capable to harvest higher power up to 60 milliwatts, and we can suggest that this low cost carbon zinc alloy can be nanomaterial can be performed better for these field applications. We have designed the electronic circuitry for harvesting a maximum current from such application based bioelectronic system. So we have tested it to eliminate our pilot premises during night time. So application of such microbiological system like it can harvest electricity during day night, and it can utilize to eliminate the pilot premises at night time, and during the rest of time we can use the electricity for generating electric current, which can be used for to charge our mobile phone batteries, as well as it can illuminate the LED bulbs and other electronic appliances. So such similar work on sludge digestion treatment has been published in 2015 in Bioresource Technology Journal. So further, we have tested different operating condition optimization for these field scale applications, and we have find that we can harvest up to 6% of Coulombic efficiency, and COD removal or organic matter removal up to 95%. And whatever the smell issues or odor issues from our normal septic tank, it has been minimized at this septic tank MFC or microwave fuel cells. They provide anaerobic oxidation of ammonia to nitrogen as well as sulfide to elemental sulfur, so the odor problem can be minimized while considering the environmental aspect. So key features like with development of this microbial fuel cell, we have tested from lab scale, we have go for scaling up as well as further for practical applications. This biotech concept can be suitable for field applications and on-site treatment of human waste, and the harvested energy or power can be made available for illuminating the toilet premises at night time, and during daytime it can be used for charging low power electronic appliances. This pilot system or biological system provides additional advantage of simultaneous organic matter removal. It can completely eliminate the pathogens with hypochlorite dosing. It can generate electricity simultaneously, and whatever electricity generated can be utilized for operating different electronic appliances. So this can be a successful demonstration of pilot plant bioelectronic system for on-site sanitation purposes. So we have come with some scaling up challenges, like we have scaled up the system from like milliliter capacity to the kiloliter capacities. So this system need to be understand very well in terms of electrochemical limitations. So this electrochemical limitations can be like, it has a limitation that individual cell can generate up to 1.1 volt, and there are several limitations from cathodic side, as most of catalytic catalysts, they have low oxygen reaction rate. So we have to work on this electronic to develop catalyst. When we are talking with biological system, it has limitations of microbiological systems at some of the microorganisms. When we are talking with mixed culture, so it has slow electron transfer rate and also substrate diffusion is quite higher for these conditions. And when we have to make such a system as a low cost technology, so selection of material as well as catalyst is one of the main aspects while going for practical applications. Other challenges like this system, we have to consider with economical challenges as we have to deal with cost as well as energy balance system, process system, and we have to compare with existing filtering tank systems. The engineering aspect, like we have to deal with the electrode spacing as well as operating parameters, and also we have to focus on the selection of material and architecture or reactor design so that we can easily allow the fluid dynamics well with uniform distribution of substrate into the anodic chamber, and it can be uniformly distributed and it has a low substrate diffusion inside the MFC. When we are considering the complexity of the system, as this microbial cell system is a multidisciplinary approach, so it needs knowledge of your biology, chemistry, your environmental engineering, electrochemistry, basic material science, as well as chemical engineering knowledge to address the whatever scaling up challenges has been come with complexity of system. And also, this complexity goes on including when we are dealing with real wastewater, like our municipal wastewater, or when we are dealing with industrial effluent, as well as waste which is having high lignosulfurous content. And also, it has some stacking up challenges, like as well as scaling up challenges. During stacking up, when we are connecting number of MFC units together, so there is problem of voltage reversal. So the cells with bigger low voltage take voltages from higher cells, and we have lost with voltages. And when we are scaling up a system from 1 liter to the 1 kiloliter, so the power is not that much proportional, like 1,000 times. So we have to work with these scaling up challenges and stacking up of different microbial fuel cells. It has different operational problems as well. So coming with outlook, so when we consider this microbial fuel cells, it has been 100 years that research has been started from that scale, but it is only limited or few studies are available, almost less than 1% that is focused on scaling up as well as practical application of microbial fuel cells. Almost like till now, more than 11,000 publications has been published, and almost less than 1%, almost 10 to 15 publications they have focused on scaling up issues of microbial fuel cells. So this study is one of the successive indicator for moving from lab scale to the practical application of microbial fuel cells for sanitation purposes. So such system can be a sustainable option for wastewater treatment as well as energy recovery from waste. So several pilot scale MFC has been developed in lab, which are a full indicator for commercialization of this technology. And this developed bioelectrical pilot system showed its practicality of MFC for real field applications. Coming to the, there's some startup companies they are coming for commercialization of microbial fuel cells, as it is one of the new upcoming technology for wastewater treatment. So there were companies from USA, Devon, Tropos, EMFC, Plant MFC, as well as from European side as well, Plant E, Netherlands, as well as some Indian companies, Indian oil corporations, they are coming for treatment of petroleum wastewater into the microbial fuel cells. And again, we have established one commercial plant at NTPC site, Noida, under NETRA project. It has a capacity of 720 liters and it is under testing purposes. We have also worked with Tata Steel for microbial desalination cells for heavy metal removal, and several companies they are coming for forward utilizing the potential of this microbial fuel cell for wastewater treatment, as well as it can be used for energy recovery purpose. And most of the scientists they are working for life cycle analysis of such practical full-scale microbial fuel cells. So coming to the perspectives, as individual MF system or any conventional wastewater treatment system is not sufficient to address or to treat the industrial effluent. So in this case, it can be coupled or it can be integrated with microbial fuel cells. So it can enhance or it can improve the energy efficiency in terms of power output as well as wastewater treatment efficiency. So it can energetically improve the wastewater treatment efficiency at field scale. So we have to understand a basic electron transfer mechanism to go deep into the horizontal direction so that we can harvest or we can promote our bacteria or microbes to harvest maximum energy from such wastewater. So nowadays, wastewater can be considered as resources rather than considering it as the only waste. So several modification can be proposed based on requirement. So there's like sediment events can be proposed, constructed wetland can be proposed, and we have to again rely on power management system. So it is one of the perspective, and still we are working with commercialization of this technique by implementing or by practically implementing such systems for on-site applications. So this concept, this biotoilet, is nothing but it has been combining our microbial fuel cell systems with septic tank systems, and in this case, we can harvest energy along with on-site treatment of septic tank waste or human waste. So such work on biotoilet has been focused in many newspapers based on this concept of biotoilet. So it has won research award from PM Modi as a Swachh Bharat award. Under this also it has published in many of newspaper as well as in publications as this biotoilet concept that generate electricity from human waste. So several publication or newspaper has highlighted the issue with the treatment of human waste. Recently, we have received Gandhian Young Technological Award in 2018 from Dr. Harshvardhan, as well as in also 2015 we have received Young Scientist Award from Dr. Mashalka sir. Also from Minister of Drinking Water and Sanitation, we have received award Swachh for Swachh Bharat Mission, and also we have received several awards as well as fellowships for this biotoilet concept. We have several research grants as well as research projects based on this biotoilet concept for treatment of human waste and generating the electricity simultaneously. And we have received some funding from NTPC to develop a biotoilet in its premises at Noida. So the work we are working on to developing such biotoilet concept. So these are several publications that I have published during my PhD work based on this treatment of wastewater into the microbial fuel cells, then biotoilet concept and optimizing different parameters in the microbial fuel cells by optimizing or by taking into consideration of different anode catalyst, cathode catalyst, membrane separator variations, as well as providing a different treatment to the anodic inoculum and developing a new anodic and cathodic catalyst for scaling up purposes. So these are several publications that we have published during this span of time. So I thank the organizing team for giving me opportunity to publish my to present my work in this in webinar. I thank Kharagpur also for allowing me to present this work here. And these are my team here from Professor Gangadhar's lab from IIT Kharagpur, Department of Civil Engineering, where we have worked with developing such concepts to develop on microfuel fuel cells. And again, thank you all the participants as well as if you have any questions, I'll be happy to answer any questions also.
Any question from anyone? Okay. Okay, thank you, Jadhav. I think there is no question. So over to Dr. Alka Dubey, ma'am, chairperson.
Thank you, Dr. Malesh. Next, participant Dr. Markandeya Singh. Dr. Markandeya Singh has completed his PhD from APS University, Lima, Pradesh, and Senior Research Fellow from National Center of Experimental Mineralogy and Petrology, University of Allahabad, UP, India. He is Associate Professor in Applied Sciences Department, Technology and Management, Gorakhpur, UP, India. He has published more than 30 papers in academic journals, like number of in-solid state and ionic societies. Today, the topic of his presentation is electrical characterization of solid polymers electrolytes. So welcome, Dr. Markandeya. Good luck for your presentations. Dr. Markandeya, please unmute your headphone also.
Dr. Markandeya, you are not audible, please. You are not audible. Please on your mic. Dr. Markandeya? Sir, you are not audible. Yes,
Hello?
yes, sir. Okay, continue, sir.
I am audible?
Yeah, you are audible and you are presenting now. So please minimize the screen and open your presentation.
Okay.
Yes. Yeah. Yes.
Good afternoon, everyone. First of all, I would like to thank organizing committee to give opportunity to share our idea about electrical characterization of solid polymer electrolyte. Basically, in this lecture, we have planned the following talks: introduction of solid state ionics, electrical characterization technique, impedance spectroscopic, and scaling properties. Basically, solid polymer electrolyte is a ionic conducting material which posing high ionic conductivity. It means fast ion conductor. It possesses the high ionic conductivity 10 power minus 6 to 10 power minus 1 Siemens per centimeter, and small ionic electronic conductivity and small electronic transference number, and high ionic transference number, it is unity. Conducting species is monovalent, like lithium ion, sodium ion, copper ion, silver ion, hydrogen ion, and anion is fluoride ion and oxygen ion. Electrolytically different from the liquid electrolyte because there is no leakage and there is no violation. This type of figure like no leakage in battery and etc. and wide temperature range operation capability in solid polymer electrolyte and shelf life. The view of solid electrolytes, solid polymer gel, batteries, capacitor, sensor, electrochemical devices, electrochromic devices, and artificial pacemaker. So these are few applications of solid polymer electrolyte. Now I'm to show you the practical application of electrolyte. Here we discuss the DC and AC conductivity of the solid polymer electrolyte. The basically AC electrolyte characteristic with the but the fast conducting it's not feasible. In fast conduction we use the AC, and AC conductivity is governed by this circuit VT is the VT equal to V naught exponential I omega t, and the impedance ZT equal to the Vt upon It is a function of time. The impedance and resistance can be seen in this figure. The resistance, basically the resistance, sample resistance, the graph is shown by this one, and capacitance and inductance, the phase of between the voltage and current is 90 degrees, and in the electrolyte sample we discuss the RC circuit. So RC circuit is R means the resistance of this spectra, so real part of the resistance, and in capacitance the imaginary part of the capacitance. So combination of RC circuit, we discussed the R by this spectra. This is the impedance RS minus I upon omega CS. So this can be discussed. The RS is the resistance of the electrolyte. So in the electrolyte sample, we discuss the sample is here, and circuit RC, we discuss the RC circuit, a complex impedance, complex resistance. The impedance is equal to the RP 1 upon RP upon plus 1 upon I omega Cp. This forms the semicircular circle, and the equation of the semicircle is given by in the form of impedance, real part and imaginary part, and adding this two by this equation we get the equation third, and equation third we give equation third we find the circle equation with the center of Rp upon R2 with the radius Rp by 2. In the impedance spectroscopy, basically we discuss the three type of resistance: bulk resistance, grain boundary, and surface of electrodes. So electrode resistance. So this is the circuit diagram of three type of resistance: bulk resistance and grain boundary resistance, and the electrolyte interface resistance. So this is the RC circuit. So in RC circuit, we plot the bulk resistance, impedance, and plot of the impedance, imaginary impedance and the real impedance. We find the semicircle. This is the equation of semicircle. So we find the semicircle, but in the electrolyte case, experimentally we find the we not find the exact semicircle. So we find the depressed semicircle, and in other case we find the line of in low frequency region. This is due to the new concept of CP, constant phase element. So depressed in constant phase element, we find the depressed semicircle. So in depressed semicircle, we find this type of result. The equation is next slide. So constant phase element is nothing but it is the hybrid resistance and capacitance circuits. In this, we calculate admittance 1 upon R equal to the impedance R equal to R upon 1 plus I omega power n A not R, where A and N are the dispersion parameter and A not equal to the 1 by R. If N equal to 1, it means the random, it gives the random motion of the ions. Here in this plot, we see that the variation of impedance, real and imaginary part, in different temperature. The radius of semicircle is decreasing with the increasing temperature. Similarly, this is another figure of the depressed semicircle. This is the equation of depressed semicircle. This is due to the roughness of the sample and the distribution of the reaction rates and variation of thickness and composition and non-uniform current distribution in the sample. So next, this is the conductivity formulation. Here we discuss the AC conductivity in this figure. AC conductivity varies with the frequency at different temperature. Here we draw a line. This shows the activation energy of at different temperature. This shows that there is a impedance relation, hopping. These are the parameters: hopping frequency, carrier concentration K, and dispersion parameter A and N. The value of dispersion parameter must be the 0 to N. These are the formulation. We can calculate the hopping frequency and the value of 0 and N. There is the two equations, Almond-based formalism and Johnson power law. We discussed the AC conductivity. There is a two region. In low frequency region, independent plateau region, and higher frequency region, it is a dependent frequency region. So we find the DC conductivity by the extrapolation of the frequency independent region, and AC conductivity increases with increase in frequency and temperature. Next, the dielectric here we discuss the dielectric formalism. Dielectric formalism is actually calculated with the data of impedance spectroscopy. The static, there is a parameter, static dielectric constant and dielectric constant and high frequency epsilon naught, dispersion parameter of alpha. So this equation can use by the devices epsilon naught equal to epsilon infinite and plus epsilon s minus epsilon infinite to divided by 1 plus I omega t. So this is the observed behavior has been fitted by the Cole-Pull formula of the form. So this is with this data we plot the dielectric constant with frequency at different temperature. So we find the low frequency region is the low frequency region, electrode polarization, and the frequency independent region, static dielectric constant, and in high frequency region it is the higher frequency.
What's the problem in the session?
I am audible? Hello?
You are audible. Please start from.
Hello?
Yes, you are audible. You are audible, sir. Continue.
So these are the formula we use in the modulus studies,
Please, your
dialectic studies.
sir, your screen not visible.
Hello?
Your screen not visible. Please again open. Your screen not visible. Please open again.
Dr. Markandeya, present your screen.
It is visible?
Not.
It is visible?
Not visible.
Please again present your screen, sir.
Sir, again you have to same procedure. Yes. Please adopt same procedure.
It is visible?
Yes, yes, it is visual.
So these are formulas we used in the dialectic studies, impedance and dialectic studies. The modulus, we adapt the modulus spectra for the suppression of the electrode polarization in the sample. In the modulus formula, electrode polarization effect clearly appeared to the vanish in contrast to the dielectric formulas when it is observed around the lower frequency region. In the modulus imaginary part of the modulus peak, we assume the related to the translational ion dynamics and mirror of the conductivity relaxation of the mobile ion. Here the formula of modulus formulas. The modulus formulas, we consider the three parameters: dielectric constant at high frequency, epsilon infinite, and conductivity relaxation and dispersion parameter beta. In this figure, we seen that at the low frequency region, the modulus tend to the very small, suggestive to the absence of the electrode polarization in the sample. With after the modulus spectroscope, with the increasing frequency, modulus increases finally reaches to the constant value and respectively of the temperature. Next, this is the imaginary part of the modulus study. Imaginary part of modulus is increases with increased frequency at the different temperature. Here we find the peak and the value of the full width at the half maximum of this peak align the single relaxation time. If we find the value of FWHM is 1.1 decades, and if we find the value of FWHM is about 1.55 and greater than, it suggests that the presence of distribution of the relaxation time in the material. Here the KWW relations. By this relation, we find the translational dynamics of the material and dynamics of the material. Here we use the scaling behavior of the sample because scaling is the best for the to find the master curve for the underlining the behavior of the ion dynamics. These studies are mainly carried out the various temperature and the composites. So we use the various type of scaling, the conductivity scaling with the frequency, and permittivity of scaling with the frequency, modulus scaling is the frequency, and impedance scaling with the frequency, and impedance scaling with the impedance. So these are the various scaling methods we use in electrical characterization. The universal scaling behavior of the conductivity spectra in ionic conduction. Here the AC conductivity varies with, in this figure we discussed the AC conductivity increases with increase in frequency and increases with increase in temperature. By this equation, we can scale our data and find the hopping frequency and AC conductivity in this sample. So we find in here we draw the line. This line indicates that the hopping frequency and DC conductivity are activated with the same activation energy. At the different temperature, we plot the value of AC with the DC conductivity with the AC conductivity and frequency characteristic frequency with the frequency. We find the single curve at the different temperature, which shows that the ion dynamics of the sample is a single master curve. Here the scaling behavior of the modulus spectra. This modulus spectra shows that the single master curve, which indicates that the suppression of the electrode polarization in low frequency region. In higher frequency region gives the different ion dynamics at a different characteristics. In ion relaxation mechanism, the temperature dependent under the modulus formalism. So we can adopt the modulus spectroscopy to vanish the electrode polarization in the sample. Thank you. Hello. Hello.
Yeah. We are okay. There is any question?
Hello.
There is any? Okay. Over to Dr. Alka ma'am.
Thank you, Nilesh, sir. Now the next presenter is Dr. Purnima Sharma. Dr. Purnima Sharma has completed her PhD in Material Sciences from MSc Baroda. Her area of interest research area papers in bracketed journal of Science Direct and its purpose, and has been a reviewer of reports. She also worked as program coordinator physics ESFC University during 2007 and 2019. Now, she is presenting on the title Polymer Nanocomposite Electrolytes, New Opportunity. Dr. Purnima, all the best.
Yes, ma'am. Thank you, ma'am. Am I audible?
Yes.
Okay.
Yes. Continue. Everything is okay.
Good afternoon, everyone. First of all, I would like to thank Dr. Nilesh Rai and AKS University to give me this opportunity. And I would also thank to all eminent speakers for the wonderful talks. Now, I'm coming to my presentation. The topic of the presentation is polymer nanocomposite electrolyte, new opportunities. Now, the broad outline of the presentation include the introduction part and then the lithium-ion battery. Then I'll discuss about solid electrolyte, the characteristics of constituents of polymer electrolyte, then the classification of polymer electrolyte, and what are the applications of polymer electrolyte. Then briefly introduce the polymer nanocomposite electrolyte. Then I'll discuss about the polymer blending and the complex impedance spectroscopy tool to study the electrical properties of polymer nanocomposite electrolyte. And after that, summarize the whole thing. Now, in the introduction part, we all are aware that the main energy requirement of ours is fulfilled by the non-renewable energy resources, which are oil, coal, natural gas, etc. And these resources are sufficient to fulfill the human's requirement for a longer period of time. but the major concern about these resources is the pollution. Now, to overcome this problem of pollution, scientists have suggested the use of renewable energy. Instead of using non-renewable energy resources, we can go for renewable energy resources, which includes the hydro energy resources, solar energy resources, wind energy, and electrochemical energy resources. So I'm going to present the electrochemical energy resources part. So in that direction, when we talk about the electrochemical energy resources, the first thing that comes in our mind is the battery. So Sony launched its first commercialized lithium-ion battery in 1991, and after 20 years, Nobel Prize for that lithium battery is given to Goodenough, Stanley, and Yoshino. Now, this image indicates the charging and discharging process for a typical lithium-ion battery. Here we can see the in the middle, that is the electrolyte part, and the cathode and anode part are equally important as we consider that to make a typical battery. Now this show how the transition has been made in the era of lithium-ion battery. In 1970, the concept of lithium-ion battery has been started, and in 1990, means after 20 years, there the commercialization of lithium-ion battery was taken place. Since there is a revolution in the field of this battery, and we are expecting lithium-ion battery in 2030. Now come to the fundamental part. Solid electrolytes are the materials in which we can say the large number of ions, that includes the cation or anion, should be mobile for the conduction, and it should have the empty and occupied sites with the lower activation energy for the jumping of electron between the sides. And the structure of the solid electrolyte should be 3D permitted by the open channels that will allow the cation to jump from one side to another side, right? And the ion should be highly polarizable. These are the basic requirement for any material to work as a solid electrolyte. Now, basically, the solid electrolytes are divided in two categories. The first one is known as the glassy electrolyte, in which different materials are taken, and then further they are used to make the glassy electrolyte. And the second category fall in the category of solid polymer electrolyte, in which a polymer is generally taken that is dissolved in a solvent, and any conducting salt is added to it to provide the conduction, right? The right image indicates the different kind of ion transition or ion movement in the polymer chain. The first one is the intra-chain hopping, in which the cation will move inside the chain from one chain to another chain, and the second one is inter-chain hopping, in which the ion will hop from one side to another in the same chain. Similar to this, the second image indicates the intra-chain hopping via the ion cluster, and the last one image indicates the inter-chain hopping via the ion cluster. It means that in the first image it shows the movement of ion, and in the second image it shows the movement of ion, or you can say the hopping of ion via the ion cluster. Now this image indicates the ionic conduction in solid polymer. The first one is the normal aqueous solution, or you can say the liquid electrolyte, in which the ion is dissociated into positive and negative charge, and the positive charge moves toward the negative electrode, and the positive charge will toward the negative. The second image indicates conduction in polymer towards the negative electrode. Now, to fulfill of polymer selection of polymer, salt, solvent, nanofiller, plastic host should have the following properties, which includes the it should have the fast segmental motion of polymer chain. It should have the low glass transition temperature. It should possess the low viscosity, high electron donor groups. If the polymer will have these properties as a polymer host in polymer electrolyte. The salt should also have these properties to work as a polymer electrolyte. The first one is the low, it should have the low lattice energy. It should have high ionic conductivity, high mobility, broad voltage stability window, low ion pair formation at high content. It should have large anionic size. It should have small cationic size. This cationic size high thermal and ion transference number. It should towards the cell component. Now next come to the solvent. We are having the polymer part, we are having the salt part. Now these two has to be dissolved in a common solvent, which should have the good solubility for polymer as well as salt. It should also possess the high dielectric constant. It should be abundant in nature, non-aqueous in nature, low melting point, low viscosity, and large flash point. Now next come to the plasticizer. Plasticizer should have low melting point, high boiling point. How composite electrolyte is nanowire, nanobelt. By the addition of these nano additives, the properties property for their particular applications. Now, based on how the polymer electrolyte is made, polymer electrolyte are classified in broadly in 4 categories. The first one is the conventional complex. Salt are dissolved in a common solvent. Next is plasticized polymer salt complex, in which a plasticizer is also added in polymer salt complex. And next to that is gel polymer electrolyte, in which the ionic liquid is added to the polymer electrolyte. And the last one is the plasticized nanocomposite polymer electrolyte, in which the nanofiller is further added to the plasticized polymer electrolyte. Now these are the few applications of polymer nanocomposite electrolytes. They can be used in electrochemical batteries, electrochemical sensor, fuel cells, supercapacitor, memory devices, high vacuum electrochemistry, electrochromic display, and many more. Now, what are polymer nanocomposite? These are the materials in which the non-inert nanofiller that are in the dimension of 10 to 100 angstrom in any one of the dimension are dispersed in an organic polymer matrix. Means if we are having a polymer, we are having a salt, and we have to add that polymer in very small amount, then we can obtain the polymer nanocomposite. These are commercially introduced by Toyota in car belt cover to improve the quality of car belt cover, which include to provide its strength, modulus, and the thermal stability. Now, further to car belt cover, it is also observed that we can the physical properties of polymer electrolyte can be improved or enhanced by using these nanofiller. This image give a virtual image how the structure of a polymer nanocomposite will look like when the nanofiller is added to the polymer matrix. These red dots will indicate the anion part, and the orange part indicates the polymer chain, and the bigger circle in blue and yellow color, that is the nanofiller. So And this is also the mechanism of ionic conduction. This is the simple aqueous or liquid solution in which the salt is dissociated. And the second image indicates the when we add the nanoparticle in the same system, how the cation will have the more pathway for the conduction, which will result in the enhancement in ionic conductivity of that material. Now for the polymer nanocomposite can be prepared by, there are various techniques available that can be prepared by the hot press technique, solution cast technique, spin coating, melt intercalation, in situ technique, dip coating, and what are the properties are influenced by adding the nanoparticle, that are the ionic conductivity, that will reduce the glass transition temperature. It also reduces the crystallinity. It increases the ionic transference number. It will give you more electrochemical stability window. It will provide the good mechanical as well as the thermal stability of the material. Now, when we think about of making any polymer electrolyte, the first thing that comes in our mind, that is the PO. That is always favorite one for any researcher to work upon. Now, why it is so? So this is basically because of characteristics of PO that include the presence of sequential polar group with large sufficient electron donor power. Because of that, the cation have more conduction inside the polymer chain. It will provide the low hindrance to the bond rotation, and there is a suitable distance between coordinating center to form multiple intra-polymers ion bonds. It has a good ability to dissolve high concentration of different salt. Now, after choosing a particular polymer, the many properties cannot be, or many desired properties cannot be fulfilled. For that, the polymer blending has come across, and it is the mixing of two or more polymer, and these two polymers are mixed with a desired property, and one can control those properties by varying the amount of the polymers which we are using, right? So for example, if we take, let me consider the case of PO, which I am going to elaborate further. In the case of PO, PMMA, PO is a semi-crystalline polymer, and PMMA is an amorphous polymer. However, the glass transition temperature of PO is around minus 50 degree, and PMA glass transition temperature is 100 degrees. So there is a huge difference between the glass transition temperature. So by blending, the glass transition temperature of the whole polymer blend can be increased to provide better result as compared to the pure PEO polymer electrolyte. So these two polymer when we blend these two polymer, in the blend, PMMA inhibits the crystallization of PEO, and these two polymers are show the good miscibility that is available in literature, and there is a large difference in the glass transition temperature. Means PMMA is having the glass transition temperature that is more than 100, and PO is having the glass transition temperature that is minus 50 degree. So by making a blend of these two polymer, a room temperature polymer electrolyte can be expected to be formed. Now next is the plasticization. Blend will provide purely a blend. Now to further improve its electrical properties, plasticizer can be added to that polymer matrix. Now basically the plasticizer provide the spacing between the polymer chain, and it will also increase its free volume. That will helpful in dissociating the ion aggregates. Now the selection of plasticizer again depend upon its properties that include the viscosity, dielectric constant, polymer plasticizer interaction, and the ion plasticizer coordination. Now in further to add on this polymer electrolyte, the nanoparticles can be dispersed in the plasticized polymer electrolytes. This will provide the mechanical stability in the film. After adding the plasticizer, it is observed that the polymer film become more brittle or it will lose its mechanical stability. So to improve the mechanical stability, also to improve its electrical properties, one can add nanofiller to the polymer electrolyte. Now this indicates how the transition in this polymer electrolyte has taken place. Initially the work on polymer, then people make the blend of it, then add salt to it, then ionic liquid, then plasticizer, microfiller, nanofiller. Now the people are working on nanoclay, nanorod, nanowire, aligned nanowire, and the recent development in the field of hybrid nanofiller. However, I am going to present about the polymer blending, and in polymer blend there is an addition of salt, then plasticizer, nanofiller, and finally the polymer nanocomposite electrolyte. So complex impedance spectroscopy tool is used for studying the electrical properties of prepared material. It ranges in between 10⁻³ means 1 millihertz to 1 megahertz. So impedance measurement includes impedance formalism, conductivity formalism, permittivity formalism, and modulus formalism. From the impedance spectroscopy, the data is received in the form of complex impedance form. From this complex impedance form, the result is converted into conductivity formalism, and further it can be calculated to find the dielectric constant and modulus of the film. These graphs indicates the system PEO, PMMA, and salt. Salt is taken is AgNO3, and PEO and PMMA polymer blend is the host polymer. Here one can see from the impedance graph, the first semicircle represents the bulk resistance of the sample, and the second semicircle represents the polarization of mobile ion at the electrolyte interface. This is the conductivity plot for the blend. On the x-axis, the PEO variation is taken, and on the y-axis, the conductivity. So one can see when we increase the concentration of PEO in PMMA, I'm talking about the blend, as we increase the amount of PEO in PMMA matrix, we have observed there is an increase in conductivity, and there is a fall in conductivity around 48% of PEO, and further there is an increase in conductivity, and again by increasing the concentration of PEO, the conductivity decreases, right? So one can conclude from these graphs that the amount by adding PEO in PMMA matrix, it will help the electric conduction, right? So it will helpful for the electric conduction, and further due to the dilution effect of PEO, the conductivity decreases. From the first graph, it is observed that around the glass transition temperature of PEO, there is a sudden sharp change in conductivity. So around that transition, the conductivity suddenly rises. So the conductivity plot is divided in two regions. The first region indicates the below the melting temperature of PEO, and the second region indicates the melting after the melting of PEO. Now these graphs indicate the variation of ionic conductivity with PEG concentration in PEO PMMA polymer host. The PEG is also added, and it is observed that by adding the PEG in PEO PMMA polymer blend, the conductivity decreases. Similar graph can be seen from the temperature dependence conductivity graph. It also indicates as we increase the amount of concentration, the conductivity decreases, while in the case of this PEG is polyethylene glycol and this EC is ethylene carbonate. As we initially increase the amount of EC, conductivity fall, and by increasing the amount of EC, the conductivity is found to increase. So at higher concentration of EC, it can be found that there can be a significant increase in the conductivity. Now in the plasticized polymer electrolyte, when we add the nanofiller Al2O3, the conductivity further increases, and this also can be observed from the temperature dependence conductivity plot. X-ray analysis characterization also support the electrical properties of prepared material, means the PO PMMA blend with plasticizer and nanofiller. It also shows that there is an increase in amorphicity with the increase of nanofiller content in the polymer, plasticized polymer. This is the another system in which we have not taken the blend. In this polymer host, we have taken only the PO polymer, and instead of using silver salt, we have used the magnesium triflate, and there is a combination of plasticizer, that is PC and DEC, and with magnesium MgO nanofiller. This is also observed that when we increase the amount of nanofiller, the electrical properties increases, or you can say the conductivity increases. That is also supported by the characterization, that is the SEM graph. One can observe from the first graph that there is a smooth curve that indicates the high crystallinity of the polymer electrolyte. As we increase the amount of nanofiller, there is a significant change in the spherulite structure of PO due to rupture in its crystalline nature. In this graph indicates the DSC thermograms, and this also support the conductivity plots of the prepared sample. Now next come to the scaling part. Scaling is also an important tool for finding the electrical conduction processes inside the polymer, or you can say any solid electrolyte. The master curve of AC conductivity is fitted according to this relation. From this relation, in polymer blend system, it is found that the most of the graph, except the second one, are making a master curve. It means the conduction process happening in all the samples, whether it is a polymer salt sample or plasticized polymer sample, or it is a plasticized nanocomposite polymer electrolyte. The conduction mechanism in all the samples is following the same mechanism. Similar graph is obtained for this PO magnesium triflate system. This is the modular study which was carried out to understand the relaxation process in polymer matrices. In summary, in PO PMMA polymer blend, XRD results indicates that this will make a good blend, and DSC results also support that result. And in electrical, conductivity plot, it is observed that there is a sudden rise in conduction near the transition temperature, that is due to the melted phase of PO. And it is also concluded that in PO PMMA polymer, PEG plasticizer does not support enhancement in conductivity. This may be due to the similar structure of PO and PEG. However, in EC plasticizer supports the enhancement in conductivity. And if we further, at higher concentration, if we use the EC plasticizer in the same matrix, it will surely can give some good results. Now, addition of nanofiller in plasticized polymer electrolyte enhances the electrical properties, and nanocomposite with also with EC plasticizer is found to be better than the polymer electrolyte with PEG. And in PO magnesium system, DSC profile indicate that the polymer nanocomposite maintain its phase and remain thermally stable up to some melting temperature of PO. And same result also support the conductivity response of the polymer nanocomposite electrolyte. These are the some references. Thank you.
Okay. Now any questions from anyone?
Yes, Dr. Nilesh, I have two questions.
Yes, sir. Yes, sir. Please ask.
My first question is, when you show the slide of the conductivity of first system, then there is a curve where PO has two peaks, one at most probably 28% and other is 60%. What is the reason of these two curves?
Sir, that can be due to the PO concentration. Initially, when we increase the PO concentration, then it supports the conductivity, and after reaching certain amount, the dilution effect of PO will not support the conduction process, and because of that, there is a fall in conductivity.
But you have not mentioned that is the composition of the PO and other mixing amount polymer.
Sir, PO, the whole polymer host is to be 100%, and the amount of PO is varied with respect to PMMA. So, sir, if PO is 10, then the PMMA is 90%.
मैडम बोल रही, मैडम का गया है अभी
second query is, why you in all the conductivity measurement curve you have multiplied the T, capital T, that is absolute temperature in y-axis? What is the reason? Are only showing the higher conductivity value or any?
No, sir, I'm not saying that this material will show the high conductivity. Instead, instead of using silver salt, if we use lithium salt or any other salt, we can expect some more amount of this.
But the multiplication of T, what is the reason? Multiplication of capital T, that is absolute temperature. What is the reason to show in all the conductivity measurement graphs?
Am I audible?
Yes.
Yeah.
Yes.
Sir, once again repeat the questions. I think.
Sir, am I audible?
Yes.
Sir, I am saying there is no particular reason for multiplying this temperature for plotting this graph. It is only for representation.
Okay. And last query, you always discuss about the nanofiller. Have you measured the average crystallite side of the formation of the electrolyte?
Sorry, sir, that we didn't.
Okay. Thank you.
Thank you, sir. So, sir, I would like to thank you again for giving this opportunity, and they are doing excellent work for researchers for organizing such wonderful webinar. Thank you, sir.
Thank you, madam. And let me extend my sincere thanks to Dr. Alka Dubey, principal at Adina Institute of Science and Technology, for this session. Thank you so much, madam, to be with us and having your kind attention for this webinar. And we would like to now invite our Pro VC, Dr. Harshvardhan Srivastava of AKS University, Satna. He will address you about this webinar and enlighten with us about the new functional physics. So please let me introduce you all with Dr. Harshvardhan, Pro VC Development, AKS University, Satna.
Hello.
Yes, sir, you are audible.
Okay.
Yes, sir. Okay, thank you, sir. You are audible.
First of all, I, on behalf of AKS University, Dr. Harshvardhan, Pro Vice Chancellor, welcomes and congratulate the Department of Physics, particularly because such a mega seminar or event was organized by the department under Dr. Nilesh Rai. It is really a wonderful thing which you have done, and I also appreciate, first of all, this is also to mention that the Department of Physics of AKS University is doing lot of things they have done in the past also, and presently they have organized a 4-day seminar on different issues which are the burning issue in the world, particularly in space science, astroscience, material science, and so many things like particle physics and solid state, etc. In of course in medical science also. So this, though you how you have selected the our keynote speaker, I believe that all are eminent speakers around the globe, and particularly I would like to mention few keynote speaker like Professor R.K. Pandey of USA, Michigan University, Professor S.A. Hashmi of Delhi University, and Professor S.A.R. Hashmi of Bhopal, and others also notable contributions they have made during last 3 days. This is third day that this seminar is going on. I believe that all the researchers, students of the country, and our students of this university also must have been benefited with this organization of seminar in such a decent way, and naturally the applied aspects must have been covered during last 3 days, and all the participants who have invited as a invited guest or keynote for the keynote address, all have contributed in the interest of the society. Everything which the scientists the scientist does, or any contribution is made from any science, that is of course in the interest of the society is to be done. So the functional approach of functional physics is to apply on all the aspects which are required today in the world, and not only in the in any city, but the research students who are doing in their lab, they must have been also benefited with this seminar. And I congratulate all the faculty members of AKS University who have their participation as a organizer as well as the listener also. Particularly, I would like to mention Dr. Nilesh Rai, Saket Kumar, Lovely Singh, Manish Agrawal, CP Singh, and Dr. Upi Tripathi, and also our IT expert, Mr. S.K. Soni, who have arranged so in such a decent way that I have heard that students have actively listened and participated in this seminar, and by and large they would be benefited with such type of activities and seminar. And I also advise the organizing committee that they must take feedback from the students, how they have been benefited, how far they have learned, and how they will apply in their future life, because future depends on our youth. So youth have to serve to the society. For that reason, I emphasize that whatever has been discussed, that should come in the letter and spirit in the interest of society. and wherever our students go, they must try to apply this knowledge in a practical way. That is our mission and vision of the university, that our students must learn whatever is going around the world, whatever the scientists are doing in different countries and in the research lab, and that should be accessible to a common man or the students who are having urge about the subject. Thank you very much for giving me your time for this in this seminar, and I believe that in future also such type of deliberations will go on, and it would be beneficial for the university as well as to our students. Thank you very much for giving me an opportunity to give thanks to our all delegates who have given their valuable time for our faculties, our scientists of this country, and definitely all the listeners or viewers who have actively associated during last 3 days. They would have a fresh look regarding the achievement of the physics and its application. Thank you very much.
Thank you so much, sir. I sincerely thanks my deep sense of appreciation and profound gratitude to our Pro VC Development, Dr. Harshvardhan Srivastav, AKS University, Satna. Now, it's my huge honor and privilege to announce our next speaker for this session, Professor R.B. Chaudhary from IIT ISM Dhanbad. I would just like to give you a brief introduction about him. Professor R.B. Chaudhary completed his MTech from National Institute of Technology, NIT Jamshedpur, and PhD degree from Punjab Technical University, PTU, Jalandhar. He has published more than 60 research papers in reputed international journals and 40 non-SCI papers in corporate journals. Several book chapters and books he has also written. He has also been editorial board member of the Repute Journal. It's my honor to invite Dr. R.B. Chaudhary. Dr. R.B. Chaudhary, you are welcome to the webinar, and his topic for today's discussion is Challenges and Opportunities in Polymeric Nano-Hybrid Materials for Electronic, Optoelectronic, Energy and Information Storage Devices. I welcome Dr. R.B. Chaudhary from IIT ISM Dhanbad.
Dr. Chaudhary, you are not audible. Sir, you are not audible. Sir, you are not audible. Please check your sound pin, speaker pin in your computer. I think it is not connected well. Sir, there is any problem? Sir, you are not able to listen me. But sir, you are not audible. Please check your mic. Your mic is on, but your earphone is not connected properly. Earphone is not working, I think. Your headphone is not working. Sir, you are not audible, sir. Sir, you are not audible. Yes, sir.
Hello, can you hear me? Hello.
हाँ sir, yes sir, you are yes, you are audible,
Okay,
sir.
now, yeah, I just want to open my presentation, PPT. Where to start
Okay.
from?
Yes, start, sir.
Okay, just a minute. नीचे में
लोगों को समझ ही नहीं आ रहा। दीदी से पूछ लीजिए ना एक बार।
पूछो फोन लो। Present now.
Yes sir, present now.
Yes sir, I'm just connecting with the PPT.
Yes. Please share your screen. Present now, then enter the screen and share now.
हेलो। अरे पीपीटी कैसे प्रेजेंट करते हैं यार? यहाँ पे पीपीटी कैसे प्रेजेंट करते हैं?
गूगल मीट में।
हाँ।
बंद कर दिया मैंने स्क्रीन को। अब बंद करने की इच्छा पता क्यों नहीं हो रही थी? Sir, are you using a Chrome, Google Chrome? Okay, sir, your presentation is open. Okay, sir, your presentation now is fine.
Just wait, sir.
Okay, okay, we are, yes. Your slide is open.
Can you see the presentation?
Yes.
Okay. I'm making it the full page.
Yes.
Can you see it properly?
Properly. Continue. Go ahead, please.
Okay, sir. Thank you very much.
Thank you.
Okay, sir. There is some network problem is there, and somebody have called someone to help to start the things.
No issue, sir.
Okay, fine. So for the first at the outset of this talk, I would like to thank Professor Nilesh Kumar for his invitation to join your webinars. And as I have been saying, every day I am just saying that you are having a large number of participants, delegates, and speakers from all around the country and abroad also. And today my talk is on the challenges and opportunity in polymeric nanohybrid materials for electronic, optoelectronics, energy, and information storage devices. Okay, I would like to let you know, this is all about my institute, Institute of Technology. Earlier it was ISM Dhanwad, that is Indian School of Mine, and it was established in 1926 by Professor Penman. It was established on the pattern of Royal School of Mine in London. So you see, this is a very old heritage of our institute, that is Indian School of Mine, which was declared as Indian School of Technology in 2004. And now this is a new development in infrastructure, buildings, and resources of the institute. Can you hear me properly, sir? Hello? Can you hear me?
Yes, sir, we can hear you.
You can hear me, sir?
Yes, sir, you are audible.
Okay, fine, sir.
Continue.
So now this is all about my department, Department of Physics. And we have a large number of departmental research group starting from nanoscience and technology, then material science, theoretical physics, laser and spectroscopy, biomedical sciences, and my research group falls under the category of nanoscience and technology, and which is known as Nanostructure Composite Materials Laboratory. Okay, so recent development in the field of polymeric materials used for different devices and systems, or you say the smart energy materials and devices, which can be shared in the market and development opportunity of the materials and technology, such as hybrid energy storage and fuel cell, three-dimensional integration, thermoelectric cooler, thermal management, thermal interface material, nanomaterials-based sensors, and etc. Now, let us first talk of the conventional optoelectronic devices. The most conventional optoelectronic devices are light-emitting diodes, which are used in display, traffic lights, data communication, and then it is a laser diodes, which is used in barcode reader, fiber optic communication. Then you have photodiodes, that is smoke detectors, CD players, remote control, etc. And then solar cells for the sake of energy conversion, and thermal hybrid solar cell collector. Now, this is the material features for eminent devices. The devices which we develop or nowadays in practice are the eminent devices, and we require to discuss the different properties and their features. So first one is the material features for informative storage devices. That is BRD, Blu-ray drive, and then CD, FD, DVD, SDD, SDC, etc., etc. You must be familiar with all the material features for optoelectronic devices are say laser diodes, light emitting diode, organic light emitting diode, polymeric light emitting diode, quantum dot light emitting diode, then white light emitting diode, etc. Then third one is the material features for energy storage devices, that is supercapacitor, rechargeable battery, and photovoltaic cell. I'm mainly dealing with this material features for energy storage devices. Next to this one is material features for electronic devices like antenna, desktop, iPad, iPhone, laptops, printed circuitry board. And last one is you have material feature for sensing devices like chemical sensor, gas sensor, biosensor, and temperature sensor. Next, we have material. Let us start with the material features for electronic devices. So this is all about the electronic devices for which we need different kind of materials. We require different kind of materials, and its desired properties are following and desired range. So if we use the antenna, we need aluminum, copper, gold, stainless steel, highly conducting metals are the properties. The property should be, the desired property of the material should be highly conductive, resistant to corrosion, lightweight, malleable, and ductile, and its range should be 7 into 10 power 7 sigma Simon per meter to 6 into 10 power 10 sigma Simon per meter. Okay. Next one is a desktop. Desktop is mostly made up of silicons, and which have the property like low cost, lightweight, and insulating behavior. And this is the desired properties, desired range of the parameters. And third one is the laptop, that is was with the insulating behavior, recyclable of the parameters. Then we have likewise iPad and aluminum, which require the materials like aluminum, glass, which should have the property like conducting behavior, recyclable, etc. Then iPhone, PCB, etc. Then we have material feature for sensing devices. Here we have different kind of sensors like chemical sensors, gas sensors, biosensor, temperature sensors, acoustic sensors, photo sensors. So in the case of chemical sensors, we use the materials preferably conducting polymers, ceramic, semiconductor-based materials, and desired properties are highly porous. It should be highly porous, good optical reflectance, wide temperature range, and high chemical stability. And this is their desired range of the parameters. Likewise, for gas sensor, we use mostly metal oxide. We are also using polymer-based materials, which is mainly the polypyrrole, polyethylene, and polyacetylene. And it should have the desired property like wide operating temperature, good mechanical stability, high stiffness, followed by some of the important parameters in the range as given here. Then we have the biosensors. For biosensor, we require the materials like ceramic of aluminum, silicon, carbide, and cesium carbon iodide, and metals and alloys of this thing. And it should have the property of thermal stability, conductance, low magnetic softness, good corrosion resistance. Likewise, temperature sensor, we require the materials like copper, then Constantan, Rn, then with wide range of wide temperature range, good conductivity, high mechanical strength, non-toxic properties. And for acoustic sensor, we require the quartz and lithium tantalite. And lastly, for the photo sensor, we require the semiconducting materials with low work function, etc. Now, materials for energy storage devices. This is the major area of the research which we are carrying in our laboratory research lab. So first one is the capacitor, that is Faradic capacitors, which require the materials of the dielectric nature, ceramic, mica, plastic, film, metal oxide, polymer, molecules, etc., and with the properties of high dielectric constant, higher operating voltage, high breakdowns. It should have the desired range of parameters like working temperature. It should work from minus 30 degree to 125 degrees Celsius, and the maximum capacitance should be less than 1 microfarad. If you come to the supercapacitor, which is also known as the electrochemical capacitor, it can use the materials like activated carbon, carbon nanofibers, graphene, carbon black, metal oxide, sulfide, metal dichalconide, ICP, that is intrinsic conducting polymers, and rare earth species. And the properties which required for the energy storage devices like supercapacitors are, it should have the highest, it should have fast charge and discharge property, it should have a better chemical reaction stability and good ionic properties and cyclic stability. The energy density should come in the range of 4 to 10 watt-hour per kg, and power density should come in the range of 2500 to 45,000 watt per kg. And cell voltage should be 3 volt, efficiency up to 95%. Lifespan is 10 to power 4 to 10 to power 5 cycles, and operating temperatures, it can be used minus 40 to 60 degrees Celsius. Now comes to the lithium, sodium, cadmium, nickel, carbon, electrode, metal oxide, and polymers as well. So it should have the property like large capacity, high energy density, electron transfer properties, high power density, long cycle life, redox activity, and these are some of the parameters which you require for the rechargeable battery. Then let us come to the photovoltaic solar cell, that is uses, which uses the materials like silicon, gallium arsenide, etc. And I should have the property like light absorption property, then semiconducting behavior, some of the range which we require for the photovoltaic cell. Then last one is the fuel cell. Fuel cell is the recent development in the for the for developing the energy storage devices. Fuel cell, it's a kind of electrochemical device which can convert chemical energy either in the form of thermal energy or mechanical energy or electrical energy. And it requires the materials like polymer, organic species, and hydrogen and methanol, molten carbonate, etc. And its parameters are that then temperature, current, voltage, etc. And conversion efficiency is 40 to 60% only, and it can work in the temperature range of 50 degrees Celsius to 1100 degrees Celsius. Okay, then let us come to the material feature for information storage devices. This requires different kind of there is a large number of information devices like Blu-ray disc, DVD, flash memory disk, and hard drive disks. And these are the different kind of materials which are used in these kind of, that is polycarbonate, silicon nitride, etc., etc. And so these are the desired properties which are expected from this for the different components of informative devices. And the types of storage is optical. These can click on the camera and the data is saved or data is stored in the form of optical information. And cost of storage is very high, of course high. Portability is easy to portable. It has limited durability and reliability is poor. Likewise, CD, DVD, flash memory, and hard disk, these have the desired properties. Then you have material features for optoelectronic devices. These are the different kind of optoelectronic devices like laser diode, light emitting diode, organic light emitting diode, polymer light emitting diode, quantum dot light emitting, different kind of materials, and these are the different properties followed by their parameters in the following range. Now let us come to this fact, that is organic light emitting diode and electrochemical capacitor or supercapacitor. In fact, materials for have many challenges in OLED fabrication and operation. These challenges are they require extreme electrochemical stability, lower electron mobility, high production cost, ionization potential, thermal stability, and this is the major reason people prefer to employ conducting polymer, that is intrinsic conducting polymers, nanocomposite, as an electron transport layer with all the above properties. Now, so why we use conducting polymers? Conducting polymers, because conducting polymers conduct electricity due to delocalization of pi electrons. And some of the example of conducting polymers are polycarbon, polypyrrole, polythiophene, polyaniline, then polyacetylene, polyindole, etc. The first reason for polymers to become conductive is that the polymer consists of alternative arrangement of single and double bonds called conjugate double bonds. And the second condition is that the polymer has to be disturbed either by removing electrons by oxidation or inserting electron by reduction into the material. So the conducting polymers provides many more potential advantage over metal. So these have the major advantage over conventional material like flexibility, low density, lightweight, biodegradable, corrosion resistance, tunable conductivity, then control shape, morphology, etc. So let's take the example of one of the polymeric component, that is proton exchange membrane, based on electrolysis for hydrogen gas production using solar panel. So this is one of the schematic incident on this solar panel. Have to dissociate the water, okay, water, and so the water is dissociated into hydrogen and oxygen, and we can store the hydrogen energy for its use in different purposes using the polymeric membrane. This is polymer based membrane. Okay, so this is the supercapacitor application. How we can use supercapacitors in different fields. We can use in transportation like auto, bus, rail, metro. Likewise, in renewable, we can use wind, solar, smart grid. We can use in cranes, forklifts, mining, construction, etc. And we can use it solid state drive and UPS also. So this is one of the schematic diagram for electrochemical performance of supercapacitors. You can see we are comparing the performance of the three energy storage devices, four energy storage devices like capacitor, supercapacitor, batteries, and fuel cells. You see the capacitors have, of course, very high specific power. Okay, nearly 1500 watt per liter to the 1 lakh, but it has very limited range of a specific energy. However, supercapacitor have wide range of specific power and better range of specific energy. So this red area, specific power and specific energy, whereas battery has relatively higher range of specific energy but lower range of specific power. But finally, the fuel cell for the energy storage devices, it has, of course, higher range of specific energy but very low, very poor specific power density. Now, what are the different performance parameters for battery, supercapacitor, and capacitor? Charge and supercapacitor require only 0.3 to 30 seconds for the same amount of the power, whereas capacitor requires further less time. Now, discharge time for battery is 0.3 to 3 hours, whereas for supercapacitor it is 0.3 to 30 seconds, and for capacitor it is 10 to the power minus 3 to 10 to the power minus 6 seconds. Energy density is, of course, better for battery, that is 10 to 100, and supercapacitor it has average 1 to 10 watt hour per kg, but for capacitor is very small. Likewise, for cycle life, the battery has cycle life up to the order of 1000, okay, and supercapacitor have cycle life of more than 50,000, whereas capacitor has more than 5 lakh thousand. Likewise, specific power, charge discharge efficiency. Okay, so this is all about one of the we have designed one of the supercapacitor material, electro materials for the development of the electrodes. So in this electrodes, the electrolytic ions can be very much accommodated into these finer pores of the electrode materials. Okay, the finer pore of the electrode materials, very fine pores are there. So the ions can be accommodated well. The distance between the two oppositely charged layers can be reduced to the values less than 100 nanometer. This distance can be reduced to very small dimension. The area of the electrodes interacting with electrolyte can be increased by using porous electrode material. So you have 100 farad to 1000 farad, whereas it has very few. Analytical study of the work which we have done, that is, say this is the XRD pattern of the hemispherical nitrogen dope carbon cells, okay, and these are the different samples which we have developed of different doping concentration, and this is the FTR spectra for different components. Likewise, see the Raman spectra for synthesized materials. Okay, the 2 theta degree, that is 2 theta degree, that is corresponding peak linkage for different range is given here, and the volume wave number is also given for the this FTIR spectra, and likewise for the Raman shift we have this thing. Now morphological study, that is how to measure the different morphological structure of the materials which we can develop in our laboratory or in your research laboratory. So you see these are the hemispherical, that is FECM image of ABC. ABC is the FECM image of hemispherical nitrogen doped carbon spheres. This is the pure in polyindole, and this is the FECM image of the composite 1, 2, 3, because this gives the best performance. Likewise, we have these are the different structures, and we have the finally GHI, the transmission electron microscope image, and here you can see clearly how the samples are having their hemispherical. All the samples are having the hemispherical shape, which is the major achievement and which is the major contribution for storing the ions in different sections of the hemispheres. Likewise, so the structural features of the hemispherical structure is that it's a kind of premium structure. That is, it has a lower profile with less expense. It provides sharp and safe protection. It can beautify straight lines and corners, and it can be augmented and integrated with stem wall. It enables to survive tornadoes and hurricanes, an effective and alternative to conventional structure. So regarding hemispherical structure of the doped carbon spheres, so it has one of the US reference support. So the reference support says the hemispherical dome structure are mostly formed out of the lightweight materials, that is polymer, preferably by plastic one and or by polycarbonate. Hence, the hemispherical dome provides a lightweight, strong and inner supports. Further, these have low maintenance, high strength, and unlimited design flexibility, which are not possible with other materials. So, if you design a polymeric composite of nano size out of hemispherical structure, it can help you to store more and more electrical charge for designing capacitor or supercapacitor. So this is the calculation of the centroid features, which is hemispherical, and you can see this is the hemispherical. A sphere has been divided into 2 parts. So if you have a simple spherical sphere, it had the 4 by volume of 3 pi r square. But if you divide it in 2 parts, its area, surface area is increased. Okay, so this is the Reagan plot of Coulombic efficiency and cyclic stability of the materials, polymeric materials which we have developed out of nitrogen doped carbon sphere. So 1, 2, 3, there are 3 samples. This is the polyindole, neat polyindole, and so these are the hemisphere. These are the Reagan plot having the increasing tendency toward the current density. Likewise, for cyclic number, it is also increasing smoothly. In some cases, it is decreasing, but in some cases, it is very much close to the requirement. Likewise, we have the cycle number and sector. So in conclusion, we would like to say that post-site tuning and the optimized of composite activity to the introduction of polyindole into macropores of hemispherical nitrogen-rich carbon sphere, leading to the conversion of macropores to mesopores resulted in augmented specific surface area. The modified morphology and enhanced specific surface area resulted in enhanced specific capacitance. The modified morphology with a higher number of seated mesoforms creation of alternative charge transportation pathways, reducing the ion diffusion with lengths. This resulted in efficient interaction between electrode and electrolyte and minimization of electrolytic resistance. The introduction of polyindole into hemispherical nitrogen-rich carbon sphere led to the promotion of charge storage into the bulk of composite electrode materials besides charge storage due to surface interaction with the electrolyte. This resulted in maximum utilization of the electrode material, leading to the amplified specific capacitance. And the balanced porosity and surface area prominently led to the higher packing density and thus leading to the obtained volumetric capacitance besides the improved gravimetric capacitance of the electrode materials. So this is the latest
So thank you so much, Chaudhary sir. Now we are about to close this session. I, Lovely Singh, being the convener of NRTFP 2020, extend a very hearty thanks to all our esteemed guests, delegates, distinguished speakers, and participants who blessed us with their presence and took out valuable time from their busy schedule. With these warm words, we move on to the end of the session. And that's all. Thank you. See you tomorrow.